Good morning. Welcome to UC Berkeley and the Agentic AI Summit. I'm Jocelyn Weber-Phipps, and I'm the Deputy Director for Berkeley RDI, and it's my pleasure to welcome you here today and also introduce to you our welcome speaker, Dean Jennifer Chase, who is also a faculty member of Electrical Engineering and Computer Science, as well as the Dean of the College of Computing, Data Science, and Society. So please join me in welcoming Jennifer to the stage.
Welcome, everyone. I see some of you still coming in, so please continue to come in and find seats. We are so thrilled to have you here at Berkeley. As Jocelyn said, I am the Dean of the relatively new college, two-year-old College of Computing, Data Science, and Society. The first new college at Berkeley since the 1960s. So... And really, in the 1960s, there was a free speech movement here, and that gave rise to the schools of journalism and public policy. And we all know what is going on now that has given rise to the College of Computing, Data Science, and Society. And you guys are many of the movers in this space. We are also really, really lucky to have the Responsible Decentralized Intelligence Center, RDI, at Berkeley, and it was founded by one of our leading lights, and that is Dawn Sung. She is amazing. She's won many, many awards and spearheaded so many things. I'm not going to go through all that. She is an EECS faculty member, and I adore her, and please help in welcoming Dawn.
Hi, everyone. Thanks for coming to the Agentic AI Summit. Thank you so much for everyone for being here this morning. We know that there has been, a little bit of having everybody set up with the badges and so on, but really welcome everyone here. Okay, so how this started, so now everybody recognizes that Agentic AI is the future of AI. But this whole effort actually started last fall, 2024, where RDI started the world's first Agentic AI MOOC, LLM Agents MOOC, where we actually had tens of thousands of students and learners enrolled globally. Back then, there were very few actually talks about agents. We are very happy that we actually started the world's first LLM Agents MOOC. And then AI, as we know, really moves really fast. So now, suddenly this year is now 2025 is a year of agents. And we're already excited about the fast advancements in frontier AI. And this really is a driving force for agentic AI. And also now, there's really thriving efforts, both horizontally and vertically, across the whole stack of agentic AI systems, with different startups and also incumbents really thriving in this space. So for this summit, thanks everyone for your great enthusiasm and excitement. As I mentioned, so the summit built on the Agents MOOC community with over 25,000 enrolled globally. And for this summit, we have over 2,000 in-person attendees. So thanks everyone for being here. And also online, we have over 10,000 online attendees as well. And so hopefully everyone can enjoy the diverse discussions, dialogues in the summit. We have lots of really exciting talks and panels, actually across two stages. This is the main stage, and also down on the plaza in the tent, we have the frontier stage. And also we have the workshop in the workshop stage on the 5th floor that you can take at the stairs or the elevators. And also we have startup spotlights as well And also we have about 100 posters who will be presenting posters during lunch and also at the reception and also with lightning talks. So the Agentic AI Summit is hosted by Berkeley RDI, as Jennifer has introduced. Berkeley RDI is an innovation center that's across campus, campus-wide, including faculty and students from different departments and schools across campus, including CDSS that Jennifer introduced, College of Engineering, and the Haas Business School and Law School, and so on. And the mission of the RDI Center is to advance the science and technology at the intersection of responsible innovation, decentralization, and AI, and make it universally accessible. And as an innovation center, RDI has a unique structure that has 3 key pillars: research, education, community, and entrepreneurship. So as I mentioned, RDI has students and faculty across campus from many different schools. And since RDI was founded, so initially the founding of RDI, actually it was one of the very few centers, research centers that actually was state-funded. And since the funding of RDI, across all 3 pillars, RDI has made significant progress. On research, the research has won over 10 Best Paper, Top Paper Awards in top conferences, and has supported also RDI Frontier Research Fellows across campus and also in other UC campuses, many of them. And also in education, as I mentioned, RDI has started the world's first MOOC in agents with over 25,000 enrolled globally, and also have educated close to 1,000 UC Berkeley students on campus as well. And the YouTube channel has over 1 million views. And also our hackathon has over 7,000 enrolled participants from over 100 countries and thousands of universities and companies. And on the entrepreneur side, the RDI also has a Berkeley Accelerator that actually has incubated over 110 global teams in 7 cohorts that would follow on funding that has raised follow-on funding over $650 million. And so with the RDI research, it spans diverse areas, including agentic AI, AI safety and security, and decentralization and AI. And I've talked about the MOOC, and we also thank the sponsors for the MOOCs, for the competitions, and so on. And also, the spring MOOC, we have the Agent competition that has both the research track and the entrepreneurship track. And the winners of the MOOC actually will be showcasing their work at the summit on the Frontier stage. And as I mentioned, also with entrepreneurship, we have the accelerator, and the new accelerator cohort will start later this fall, so please stay tuned. So with that, so everybody can see the agenda of the Agentic Summit, AI Summit on the website. We have 3 main stages. So for the main stage, that is here, and also, given that we have a lot of people, there will also be a overflow main stage at the alumni house. You can follow the signs to the alumni house. And on this stage, hopefully, you can actually get a really great overview of different layers of the agentic AI stack, from infrastructure, framework stacks, foundations, and also to application levels. And on the Frontier stage, which is downstairs, at the plaza, in the middle plaza, in the tent, you can hear focus talks on a diverse cutting-edge range of topics in agentic AI, and also the poster sessions. The posters will be there as well as outside in the lobby. And also, we have really exciting workshops on the 5th floor from different leading companies in the agentic AI space. So please check out workshops as well.
Thank you, Dawn, for that introduction. And just to summarize, so you all understand like the logistics for today, you're currently on the third floor. This is the main stage of the Poly Ballroom. And as Dawn mentioned, we do have an overflow area, which is in the Alumni House. If you look on Google Maps for the Alumni House, you'll find it easily. It's just a like 2-minute walk from here. And then if you took the elevators out here or the stairs, you could get up to the 5th floor, 2 more floors up for the workshops, which will be going on most of the day, and that is on the website in terms of the schedule. And then just downstairs from the 3rd floor to the 1st floor, you will find the tent on the Sproul Plaza, Lower Sproul Plaza here to the west side. And then lunch will be served up by the workshops. There's a number of lunches out there. There's 2 beautiful patios to enjoy lunches up there. And there will also be lunches served on this patio and in the Frontier Stage tent. So lots of options to enjoy lunch. And you can also carry your lunch to a bench or anywhere. And we will have a reception this evening at 5:45, and that will be in the tent on Lower Sproul Plaza. And then finally, bathrooms, 2nd floor, 4th floor, and 5th floor, not on this floor. Okay, so just to be sure for everyone that you have your logistics. There's plenty of volunteers walking around today, young students who can help you also with these directions. But with that, I will turn it back over to Dawn.
Great, thanks everyone. So now we are going to start our next, and also we want to thank our sponsors for supporting this. And now we are going to start our first session in the morning. Can we load the slides? Can we load up the slides? Okay, great. Yes, so this morning the first session is building infrastructure for agents. So first let me welcome our keynote speaker, Bill Daly. So Bill is a chief scientist from NVIDIA. And also SVP at NVIDIA. And Bill is someone who actually doesn't need an introduction, has been a pioneer and has done so much influential work in architecture and in particular driving the advancement of architecture for GPUs at NVIDIA, which is providing the powerhouse for AI and agentic AI. Let's welcome Bill.
Thank you, Dawn. So it's a real fun time to be playing with hardware these days. And since the topic of this conference is agents, I thought I would give you an example of an agent that one of our folks in our Toronto AI lab built. It's called Agentic, and it's basically a second-year graduate student doing computational chemistry. So if you have a question like what is the activation energy of caffeine, caffeine being very important to me this morning, you can give it this question, and you see the hierarchy of agents there, that little tree structure. Each of them, is an LLM with some state that's been, through a combination of fine-tuning and a prompt, given a task. So it will figure out how to generate the geometry of the molecule, optimize the geometry, submit a Slurm job to run a densital functional theory computation to actually do the calculation, and then post-process that and ultimately give you the answer. And this is an example of what you can do, with agents. So let's zoom in a little bit. And each one of those agents in the tree, the heavy work is done with the LLM, possibly with a chain of thought or tree of thought to give it some reasoning performance. But it's also very effective because it has tools, right? So the tools are, running the quantum chemistry simulation or doing a geometry optimization. But a tool can be as simple as a calculator. If you want a LLM to do some calculations for you, you're better off with like a 1 billion parameter model attached to a calculator than you are with a trillion parameter model trying to do that calculation just with the language. And so it's a very powerful thing to take that LLM and couple it with a little bit of internal state and memory and a policy and a bunch of tools that can be accessed. But this session is about infrastructure. Let's talk about what it takes to run one of these agentic models. And I'll start with some motivation. Deep learning really takes 3 things. It requires algorithms, as illustrated by the figure from the AlexNet paper on the bottom here. It requires data, as illustrated by the ImageNet photo on the upper right. And it requires hardware. You can think of this as sort of air, fuel, and spark, right? Once you have the air and the fuel, you need the spark to ignite it. So the thing that was here first, think of this as the air, were the algorithms. Deep neural networks, convolutional neural networks, training them with stochastic gradient descent and backpropagation were all known in the 1980s. In fact, I took a course when I was a graduate student at Caltech from John Hopfield in 1984, where I learned all this stuff. I got to build these neat little models, have them do really toy problems, and I concluded that this will never be practical because it requires so much more compute than we have today. Well, things have come a long way since 1984. We have a lot more compute, but the algorithms were around in the 1980s. The data started coming around in the early 2000s with the Pascal data set and then the ImageNet data set. And so they were around still for roughly a decade before things really took off. The spark that ignited that air and the fuel that were sort of sitting around waiting for the last missing ingredient was hardware that was fast enough to train a reasonable sized model on a reasonable sized data set in a reasonable amount of time. In this case, the AlexNet model on the ImageNet data set in roughly 2 weeks. And that was done with a pair of our Fermi generation GPUs. And then things really took off. And the way they took off is a factor of 10 million over the last decade in terms of the number of floating point operations required to train a state-of-the-art model. And there are really two very distinct trends. I could have drawn one line through the whole thing. You can draw a line through any set of points. But there are really two distinct trends here. During sort of the era of people building vision models, which is sort of the blue line here, starting with AlexNet and running up through ResNet and things like that, the growth rate was about 3 times per year. And even that is a pretty heavy lift. But since the Attention is All You Need paper came out in 2017 and people started building transformer-based models, the slope has been 16x per year, which is very, very tough to keep up with. And so as the people who build the bulk of the hardware that's used to train these models, we feel a big responsibility because in many ways the advancement of models is gated by the performance of hardware available to train them. And we feel a lot of pressure each generation to increase the performance both of a single GPU and the ability to scale up to more GPUs to meet that. So how did we do that? So this plot sort of shows the evolution of NVIDIA hardware for running deep learning over basically the last 12 years. And Blackwell is up enough that I didn't want to distort the rest of the graph by putting it on there, but it's up at 20,000 equivalent tera operations per second. We started with the bottom left corner here is our Kepler generation. This is actually the GPU after the one that was used to train AlexNet. That was the Fermi generation. Each GPU is named after a scientist. And Kepler wasn't designed to do AI. When we really made the decisions and locked down what was going to be in Kepler, we were focused on computer graphics, which needs 32-bit floating point, and scientific computing, which needs 64-bit floating point. And both of those are vast overkill for deep learning. But I kicked off our first project, actually before the Keplers were around. I kicked it off in late 2010 to basically replicate Andrew Ng's experiment finding cats on the internet on GPUs. And in doing that, we really convinced ourselves AI was going to be a big thing. We needed to start putting features into our GPUs for AI. So in the next generation, it was too late to catch Kepler at that point, but the next generation we put in support for 16-bit floating point and also put in dot product instructions. And I'll explain a little bit why that's important later. And so in the Maxwell and Pascal generation, it's really the same core GPU architecture. We had FP16. The next big jump happened in the Volta generation, where we realized that we really had to start amortizing out more of the cost of an instruction. Dot product was an improvement over floating multiply add, but matrix multiply was an even bigger improvement. So we put matrix multiply instructions into Volta. The HMMA, half precision matrix multiply accumulate instruction, multiplies 2 FP16 4x4 matrices together and sums the result into an FP32 matrix. The marketing people didn't like HMMA, so they called it tensor core. And then in the Turing generation, we had the integer matrix multiply accumulate instruction. In the Ampere generation, we added sparsity, and in Hopper, we added FP8 and in Blackwell, FP4. So where does the performance come from? And it's interesting because during the period of time when everybody was using CPUs, the bulk of the performance came from process technology. Moore's law was really about process technology, allowing you to build a faster CPU, basically doubling the performance every couple years. That has been dead for probably close to 20 years. And really, it died with the end of Dennard scaling, the constant field scaling of devices in 2005, when we stopped scaling supply voltage with gate length. And so over this entire period of time, from Kepler through Blackwell, what we've gotten from process technology is a factor of about 3x out of a total of about 4,000x. So where does the rest of that come from? Well, the single biggest gain in performance has come from number representation. So starting with FP32 in the Kepler generation and going down to FP4 in Blackwell has given us a factor of 32x. And to go to the int8 in FP8 in Hopper has given us a factor of 16x. And it's quadratic, because when you do these operations, the dominant operation is multiply, and when you do a multiply, think about doing long multiplication by hand, you generate an array of partial products. So you have a number of partial products that's quadratic in the number of bits in the operands, and so the energy of the multiplies goes quadratically. The next biggest gain has been coming up with complex instructions. I'm actually going to jump ahead a slide, and then hopefully I'll be able to back up. If you look at how much energy it takes to do, and I've normalized all this to 45 nanometers to sort of not leak any information. Our energy numbers now are like an order of magnitude smaller than these. But anyway, to do a half-precision floating multiply add, an FP16 floating multiply add in 45 nanometers takes about 1.5 picojoules of energy. But to fetch that instruction, decode it, fetch the operands, and store the results takes about 30 picojoules of energy. So the overhead is 2,000%. You're spending 20 times as much energy on overhead than you are doing the operation, kind of like a big corporation. If instead of doing a single floating multiply add, you do a dot product, now instead of doing 2 arithmetic operations, you're doing 8, right? So I've reduced that overhead by amortizing it from 20x to 5x. And continuing this, when you do the matrix multiply instructions, with the half-precision matrix multiply, the overhead is now just 20%, 22%, and with the integer matrix multiply instruction, that's actually doing 1,024 operations on a single instruction, it's down to 16%. And in today's GPUs, that number's around 11%. So we've worked really hard to amortize the cost of instruction overhead out. And if you look at that over this chart of where the gains have come from, that's given about 12.5x, right? Not as big as the 32x from number representation, but still a very, very big factor. You multiply those together, and that's almost a 400x improvement. Then comes process technology that's given us a 3x from Kepler through Blackwell, and that's going from 28 nanometers down to 4 nanometers. And if you look at this chart, it's actually color-coded. It's hard for me on the monitor to see, but the black is 28 nanometers, the green is 16 nanometers, Ampere is I'm trying to remember, 7, and then we have 5 and 4. And so going all the way from 28 nanometers to 4 nanometers, only a 3x gain in energy per operation. Going to the Ampere generation, we introduced sparsity, that we can basically as long as you insist that out of every 4 elements of your matrix, no more than 2 of them are non-zero, we have very efficient implementation of structured sparsity, and that gives us a 2x boost in performance. And then on Blackwell, it's cheating a little bit, but it's really 2 GPUs. We have 2 reticle limited die that are on one package that we call one GPU. And so we essentially doubled the performance by doing that. It did not improve the performance per watt, though. So I talked about complex instructions. The other thing we had to do, so we basically got essentially 1,000x of that 10 million that we needed to support the growth in model demand for training from making the GPUs better. The other 10,000-fold comes from using more GPUs. And there's several axes to the parallelism that we use here. The first split is between data parallelism, which is sort of into the page on this chart, and model parallelism, which is the x and y axes on this chart. Data parallelism is easy. You take your training data set and you break it up into batches, and you dole these batches out to different groups of GPUs, and they basically operate independently. So it requires very little communication to do this, and relatively modest synchronization overhead to do this. And then when you finish a batch, everybody sends their results together, so you can sort of combine the difference in weights from that one batch to the next. So everybody learns not just from their batch, but from everybody else's batch as well, and then you do the next set of batches. So data parallelism is easy. What's harder, but which you need to do also these days, is model parallelism. And model parallelism here we split across two axes as well. The first is pipeline parallelism, which is the y-axis here. So if you think about a typical transformer architecture, you have a number of layers. You know, Llama 70B, I think, has 80 layers. And so you can basically take some number of layers, put them on one set of GPUs, some number of layers, put them on the next set of GPUs, and pipeline the activations through those. And then within each layer, you can do tensor parallelism. You take the matrix multiply you're doing, and you basically split that matrix up over a number of GPUs to get more parallelism. So by doing these things, we've gone over the years from training AlexNet on a pair of GPUs to a typical training cluster these days, maybe 100,000 GPUs running a single training job to train a, there's no way that I have talked for 15 minutes already. You need to start my timer when I started, not when I was supposed to have started. I understand how Berkeley Standard Time works here. Let me talk a little bit about software. So anybody can build a matrix multiplier. Back when I used to teach the introductory logic design course at Stanford, I think I could have assigned it to my class, and they would produced a pretty good matrix multiplier within a week. But it takes a lot of software to make it useful. In NVIDIA, we provide the software stack starting from the lowest layers, cuDNN, and then TensorRT that does the scheduling and packs layers of models together to avoid overheads. And then finally, verticals for things like self-driving cars and robotics and computer vision. But it's also critical to think that over time, the software actually improves the performance, because it's really critical that you get the software very, very fine-tuned and correct. And one good way of measuring performance here is to look at the MLPerf benchmark set. I think it's really it's an independent agency that publishes benchmarks and has pretty good rules about how to run them. And so people who make vast performance claims and don't have MLPerf results, I tend not to believe. But from one generation of MLPerf to the next, which is typically over a 6-month period, we'll see things like a 2.5x improvement in performance on the same hardware by improving the software. And this gives you an idea of how critical good software is for this. So let me, in whatever time I have remaining, which I think is more like 10 minutes, let me talk a little bit about future direction. So one thing we do to try to focus our efforts on where to put effort is to look at the best we can do today and ask, where is the energy going? And this is a pie chart, not from a GPU, but actually from an accelerator we build in NVIDIA research. And what you can see is most of the energy, that big blue area on the left side, goes to math. So basically we still have to make the math better, and that means better number representation, exploiting sparsity, not just on activations like we do today, but not just on weights as we do today, but on activations as well, and also more aggressive sparsity. And then the things on the other side have to do with memory and data movement, and there are a number of things we can do there as well. So let me present a couple snippets, and then I'll wrap up, since the timekeepers here are not letting me do Berkeley Standard Time. One big message is that whatever number representation you pick, you want to make sure you fit the set of data you have to represent with that representation correctly. And what most people do is shown on the left side here, where they take the biggest number they need to represent and the smallest number they need to represent, and they pick a scale factor that fits that range of numbers into their number system. And if you do this, you have very large quantization noise, and you have no clipping noise because you're not clipping. The other option you have is to say, well, these really big numbers and really small numbers are outliers. Let's forget about them. Let's pick a maximum and minimum that are much tighter. And if we do this, my quantization noise goes way down. But now I've introduced some clipping noise. And you can pose this as an optimization problem. I won't go into the math here. But if you look at the graphs, on the very far right side of these graphs is what most people do, where you represent the whole number line. So you have a lot of quantization noise, very little clipping noise. And as I move to the left, I basically am trading quantization noise for clipping noise to the point where they're both equal, and that's the minimum point on each of these curves. And if you look, say at the upper right graph here, the weight layer at 45, you're actually getting the same mean squared error that you would get with 4 bits that you would normally take 6 bits to get. So you're basically getting 2 bits of precision by doing optimal clipping. Another thing you can do is decide what set of numbers you're going to scale. And the way NVFP4 works, the way we're able to get performance out of 4-bit floating point, even for training, is by, instead of scaling a whole layer, which is what's conventionally done, we scale a vector of 16 elements. So with a smaller set of things to scale, we can basically scale it much more effectively and get much better performance. So let me talk about the interesting stuff before they drag me off the stage here. So if you look at LLM inference, there are really two very distinct phases. The first is a prefill phase, or context phase, where I take the entire prompt, not just the prompt you typed in, but that and the system prompt and any documents that were loaded by RAG. And there's an enormous amount of parallelism as I process all those tokens at once to produce the contents of the KV cache and the first output token, in this case, yes. But then I get into the decode phase, which is an autoregressive phase. Every token depends on the preceding token, and I've got to go through all 80 layers if it's Llama 70B and more for some other models. And it's very latency sensitive, and it's also very bandwidth sensitive because I have to read the entire model for each token. Every one of those 70 billion or 405 billion parameters has to be read. And these days, you don't just do that once, but before you give a token to the user, I go through a chain of thought, running that LLM multiple times, or even a tree of thought where I'll do things in parallel and then prune down what my final answer is. Let me skip over the agent here. And what this does is it really drives very different demands for the hardware you use for the decode phase, the prefill phase, which is very math limited, right? You have lots of parallelism. You can batch things up. You can crunch these tokens out. And it's not very sensitive to latency. And the decode phase, where because it's autoregressive, it's very bandwidth limited. I got to read the whole model every token, and very sensitive to latency. And so it drives very different demands, and you see deviation in the hardware generations for things that are optimized for prefill and optimized for decode. The other thing you have to be aware of is that models are constantly evolving. This is some figures from the DeepSeek paper. The Kimi stuff just came out. And people are coming up with really clever ways of optimizing the attention process, using mixture of experts so you can have a trillion parameter model but only touch maybe 20 billion parameters on each token that goes through. And by doing this, it means you need very programmable architectures. You don't want to hardwire your stuff, or somebody will come up with a model that you can't run. So let me wrap up here. I don't think I've used a full 20 minutes. We started late. They're trying to get on time by cutting my time short, and I don't like that. So anyway, to wrap up, deep learning was enabled by hardware. We had the air in the fuel, the algorithms and the data, and it wasn't until the GPUs came along and provided that spark to ignite that mixture and start our current AI revolution. Since then, we've been gaining progress in deep learning because it's taken ever more capable hardware to train these larger models on larger data sets, a growth of 10 to the 7th in demand over a 10-year period. The way we've done this is we've increased the performance of single GPUs by 1,000x in 10 years and by about 4,000x in 12 years. And this has mostly been through number representation and complex operations. Process technologies played a very small role. Software is absolutely critical to make these things usable and to realize the performance of that hardware. And I've given you some glimpses of things that we're doing to do more with less, including optimal clipping, vector scaling, and I had to skip over the sparsity. And so the current challenges I think we're facing is with disaggregated inference, figuring out how to handle the decode phase, which really stresses our current hardware in terms of latency and bandwidth, and then being able to handle chain of thought and tree of thought and agentic models that really drive up not just the amount of computation, but really also the demands on throughput, because if for every token you give the user, I've got to run 10 tokens through a chain of thought. That means if I want to deliver 100 tokens per second to a user, I've got to have hardware that can do 1,000 tokens per second. And we have to do all of this in an environment where every day we see papers popping up on arXiv with clever models, new ways of doing attention, and things that really require that we be agile and have very programmable hardware. So thank you very much.
Awesome. Thank you, Bill, for a very elucidating talk. So I get the pleasure of introducing Ramin, CVP at AMD, for his lightning talk. So we'll do 3 rounds of 3 7-minute talks, and then we'll proceed to a panel, talk about infrastructure for agents.
Thank you. I'll be happy to make up for Bill's time. So, we are entering, no, it's not displaying here. We are entering a new era in computing, and it's not what we have seen for the past couple of years. It's not the generative AI era. It's really the agentic system era that perceives, plans, and also acts. And when you think about it, this is really how the human brain functions. The human brain is not about generating or even just talking. It's a combination of agents that we have in our frontal lobe, the back, the side of the brain. And those are agents that can reason in the frontal cortex, that can perceive close to the ears, the eyes, the touch, the smell, and so on, and that can direct our limbs to act. And that's really what agentic AI is all about. It really mimics more of a human brain than just generative AI. And of course, there is a feedback loop to learn from what your interaction in nature are. But in the case of agentic AI, it could be multiple objects at the edge, could be drones, could be cars, could be robots, that basically communicate, discover each other, communicate with each other. They have small brains that can take decisions, talk to tools, and also can talk to the cloud when they need the big brains. And there is a learning step, but really the main workload is inference. It's inference and also using the tools. So inference at scale is really what is needed in terms of infrastructure for agentic AI, and also the toolings that actually run on CPUs. So we're seeing huge adoption, not just at the edge and the endpoint, but also on the CPU side, the adoption is picking back up because we have millions and soon billions of agents basically calling those tools. So those are databases, calculators, and tools like that are being used by those millions and billions of agents. And of course, context memory is going to be much, much bigger in the agentic era than it's been in the generative era. And that's why we're building the full spectrum of hardware to support this agentic AI. So for the cloud, it's clear. It's the big brain. So we have GPUs that are basically inferring GPT-4o, XAI, and other big LLMs, frontier LLMs. On the endpoint, we have, for example, laptops that have inference processing units that are powering Copilot+. So if you have an NPU in your laptop, you can do things like live transcription and translation, which is something that won't happen if you don't have an NPU. So there is a Microsoft Windows tool for that. It's, I think, live transcription is the name where if someone talks or you're playing a YouTube video, it can translate and transcribe live using the NPU. At the edge, we actually have some really, really, really interesting use cases with AI at the edge. Obviously, autonomous cars, like for example, Subaru has a little AMD Xilinx SoC for the past actually 3 generations. Eyesight is powered by an SoC, which is not an ASIC, it's just an off-the-shelf SoC running computer vision first and now AI. And we have medical devices that use little SoCs that accelerate AI. The one that I like the most is Illumina, that's running genome analytics to quickly determine what's the root cause of a newborn baby that's born sick and only has a few hours to live unless you can root cause the problem and treat it. And literally, we're accelerating that genome analytics from days to minutes, and literally saving babies' lives in the hospital because of that. And among my favorite one also at the edge are the CERN, the Large Hadron Collider, also uses a little SoC to gather the massive data coming from high-speed proton collision to discover new particles. So the Higgs boson, for example, was discovered with a little AMD SoC several years ago, actually doing AI. The CERN has programmed those devices to do AI. And finally, the fun fact is we have one of those AI chips also on Mars right now running around in the rover, which is also a self-driving car. So it's not just the big brain in the data center. The edge use cases are exploding. And on the endpoint with the Copilot plus PCs and things like that as well. And Agentic AI will use all of that together. So the communication is happening between those devices. And it's just a matter of enabling the software. So you have little container agents in the devices at the edge, in the endpoint, in the cloud, all discovering each other and communicating with each other. So software enablement is really important. And we believe that the AI era really should be open and collaborative. So our entire software stack is completely based on open source. So we're working with these partners and a lot more that I cannot fit in this slide. And basically from the very bottom kernel development to the very top pipeline building, it's all open source based. Kernel development is OpenAI Triton, which is an open source software that's completely GPU agnostic. You can write your kernel there and the compiler optimizes it, and you can go all the way up the stack. And that's how we're reshaping the compute era, basically, by building the full spectrum of compute hardware and enabling it with open source. Thank you.
Awesome. Thank you, Ramin. I now have the pleasure of introducing Trun Lee, who's Chief Scientific Officer at Lambda Compute, Lambda Labs.
Hi. Thanks for having me here, and a great pleasure to be here and talk about the infrastructure and agents. I'm just going to run a very quick thought experiment with you. What if agents were human? And how does that help us think about the infrastructure? Try to. Wait. OK. So over the past many years, human society has built a great amount of infrastructure that empowered human. So the question is, what can we build to also empower agents? This is interesting because AI agents and human are somewhat similar, but also different. They have digital neurons. They were trained with human-generated data. They are aligned with human instructions. However, they are machines. They can run much faster with higher precision. And also, they can memorize a lot of things that we can. So the question is, what can we learn from the past experience of building those infrastructure for human so to help us imagine a world of AI? I'm going to make a bunch of analogies here. But let me start from one of the most important infrastructure in our life, utilities, like water, electricity. So AI agents also need utility. Data is in the field, compute is in the electricity. We will build like data centers and power stations for sure, but at the same time, efficiency is very important. We want the power efficiency. It's always nice to have better flow per watt. And also, there's a paradigm shift from just make compute more efficient to also make data movement more efficient, as Bill mentioned earlier in the talk. And LLM in particular has long text window. You have to fetch data from different places, different memory hierarchies, different chips, sometimes even from disks. We also want operational efficiency. Cloud vendor like Lambda and Foundry, we work really hard to provide cost-effective cloud solutions, slice and dice resource for different use cases, training, inference, running agentic applications. We also want to embrace federating those resources across different regions, different clouds, and provide managed experience on top of Slurm Kubernetes, so to further improve the efficiency of using those compute. We also want data efficiency. We want all the data in the same place, ideally. We want cheap storage, fast query. We want running AI ML together with business intelligence. Also, we want to support the multimodal. Last but not least, we want model efficiency. We want to support people to build their own model with their own data. We want to use model routing to connect the right model with the right task and avoid wasting compute on basically overthinking on a simple problem. And also to call back what Bill said earlier, you want a small model to use tools instead of a huge model to do everything internally. Another very important infrastructure in your life is communication. Humans use communication to collaborate. I believe so do agent. And the good communication comes from good user experience. For example, humans need sub 200 millisecond latency to have a good interactive experience. And we sort of lose our attention if we have to wait for more than a few seconds. And we are not very good with multitask. We just it's very expensive for us to do a context switch. On the other hand, there are a lot of web servers that are non-human facing already running at a much lower latency. And the agents are great with multitasking. They can run many jobs in parallel or synchronously. So sometimes you can argue maybe time to last token is more important than time to first token. Agent can also process a lot of information in one session. So high memory capacity and bandwidth is going to be super helpful here. We also want a good user interface. Currently, natural language is being used as the first-class interface to connect an agent with different tools. But down the road, when agents step into a real world, they have to see, to hear, to sense in order to take actions. So true multimodal MCP is going to be crucially important here on the protocol level. Our society also has a strong foundation to educate, recruit, and grow workforce. The same thing can be imagined for agent. We need a platform to train, eval, and improve them. Now, I would argue that eval is probably one of the most challenging and underrated steps in this process. Just imagine how much work you would put into recruiting the right people for your team and find your ideal partner for your startup. This is the sort of effort you want to put into eval your agent. At the same time, static leaderboard eval is kind of useful in the sense that they are guardrails and lighthouse, but lighthouse is not where our destination is. We want to accomplish a real-world project, so it's important to embody those evaluation into your project and see where the gap is and try to close that gap. There's performance, there's also cultural fitness and compliance. It's been noticed that integrating agent in a vibe setting is easier. A lot of enterprise-level adaptation for vibe coding, vibe research is already happening. But on the other hand, once you incorporate agent into your core business, once they start to touch your business data, internal tools, and generate external-facing service that run at the stake, there's a lot of security, safety, and other compliance kick in, making things harder. We can keep imagining what would be a good health system for agent, what would be a good finance system for agent. Currently, token is used as a currency for AI, but that currency has been deflating quite a lot over the past years. So what's the implication of that to the sustainability of AI system? If a token is a currency, who are the banks and who should play the role of Fed? Human can also generate token. Can we pay agent by human feedback? If that's the case, what's the exchange rate between human token and agent token? I just want to finish the talk by saying I'm really, really impressed by the self-driving cars on the street in San Francisco. To me, we can learn a lot from how people build them and deploy them. They are, in essence, agents that integrated smoothly into our life. We didn't really change anything on the street for them. They just fit in. Or should we change something for them? What would the street look like if all the cars become self-driving cars? And I'll leave that for your own imagination. Thanks.
Awesome. All right, so I'll now go ahead and give the last lightning talk here, and then we'll proceed to the panel. Great. All right, so I'm going to give a talk about this framework that we've been building, myself and a number of collaborators spanning Berkeley, the Skylab, Stanford, NVIDIA, and many other companies. It's a framework we've been building to kind of make this concept of horizontal inference time scaling easier, or building multi-agentic systems maybe as a kind of more buzzwordy way to put it. And I guess the key point is we found, starting early last year, that if you kind of ensemble these LLM calls and you build networks out of these network calls, then you can actually push the quality and reliability frontier quite a bit. And I think we're starting to see these ideas manifest in systems like Grok 4, Heavy, Google with parallel thinking and Google DeepThink, 2.5 Pro Gemini. And so I think you're starting to see these things make their way to the fore, but we're still very, very early. There's a quality and reliability frontier expansion element, but there's also a price performance kind of cost reduction element. So can you ensemble calls to cheaper models and actually outperform larger models? Turns out you can, and to a very dramatic degree. So this framework with collaborators from IBM Research, Microsoft, as I mentioned, Berkeley, sponsored largely by help from Skylab, Berkeley Skylab. So first I'll actually just motivate why this inference time scaling architecture research, like why is this even an interesting domain? What are some of the intuitions that motivate this? And yeah, as Tron mentioned, the cost of tokens has been deflating pretty dramatically. The cost to achieve the same level of intelligence, the same score on some of these benchmarks, has been going down 10x every year for the past 3 years. It's gone down 1,000x. It's quite dramatic. This is a trend, a pretty rare trend. At the same time, the model ecosystem has expanded pretty dramatically. A couple of years ago, there were only a couple of models. OpenAI's GPT 3.5 and GPT-4, for example. And any routing research was just among these two options. Now there's a very heterogeneous and diverse and variegated set of model options across many, many providers. And many times these generations of models, like the Claude 4 generation, actually come out with multiple models at once. Kind of a small, cheap, fast variant, and then a heavy, smarter variant, right? And so there's this kind of notion of a Pareto frontier that's being defined. And in fact, actually, Gemini very explicitly invokes the notion of a Pareto frontier whenever they release their Pro all the way down to Flash or Flash Lite kind of family of models. And so, there is this ecosystem, there is this landscape, and there's some notion of a frontier in this landscape. And these facts have motivated a lot of work on trying to understand the landscape. To that point I made about cutting costs, the difference in prices across these different models is actually quite dramatic. O1 Pro, for example, was $150 per million input tokens versus 3 cents depending on cache hit on DeepSeek R1. So that's a 5,000x, more than 5,000x difference. That's extremely dramatic. And so you can make 5 R1 calls, compose them in some way, and actually, that would be cheaper than a single O1 Pro call. That's obviously changing. These models like O3 and such sometimes are actually cheaper than O1 Pro, but you get the idea. And so this has motivated a lot of work on routing systems like Frugal GPT, on kind of creating ensembles of network calls and aggregating in various ways. So like voting-based aggregation, best of n graphs, verifier prover structures, and some of those kind of classical ideas, that came up in neural network research around skip connections, or around GAN type structures with some almost prover verifier, discriminator generator. These ideas are actually coming back in interesting ways at this network call composition level. And yeah, so I won't go too much into this today. I'll just note these kind of facts, and also facts around specification and kind of the reliability, motivated some work on this framework called Ember. And I'll make one point about this, actually, since we have a few minutes. I think right now, arguably, the GPT-4 moment was kind of like the Wright brothers' Kitty Hawk moment. It was very, very exciting. I think it galvanized the entire field, but it's still the very early days. It took about 10 years to go from Kitty Hawk to the dawn of commercial aviation with Yanis. It took quite a while, and there were a lot of inventions and innovations were necessary to get from early demonstration of the technology to a very reliable infrastructure that could fly hundreds of millions of people per year. And so that motivated this work on Ember largely motivated by, for example, Jan Stoika's work on specifications and others. And the idea was to build a framework that kind of achieves for this network of networks composition research endeavor what Torch helped contribute for neural network composition endeavors in the 2010s. It made it, Torch made it very, very easy to compose, and kind of express new ideas, and also made those new ideas run fast with parallel dispatch and, some nice ideas undergirding it that were abstracted from the researcher. And so Ember is similarly trying to be fast to run, fast to write. This is actually a kind of banner from the Spark days. And Ember is actually named in that same family: Spark, Array, Ember. It's a funny naming scheme. And just to give you a little bit of an intuition, these are the types of things that people do. There's kind of 3 different ways that people express these Ember graphs. This is the very simplest. It's kind of a Unix X expression, very, very short. It's basically, you can have an ensemble with 101 members, some certain model like GPT-4o, and then some temperature. And then you define that in a single line, and then you can reuse that system. And underneath, those calls are dispatched across providers in parallel, and the answer is returned quite a bit faster than if it was run as just a for loop. People have also defined these kind of hierarchical graphs where you can have a graph with multiple different sub kind of trees that themselves are spread across multiple providers. And here's kind of an even more intuitive class-based way of showing it, where you can have an ensemble class that is JITted, so it can, so an IR can be composed that can be run client-side or server-side. So you can optimize execution of this graph over API calls, or if you're running things like VLM or SGLang locally, intelligently. And you can define ensembles, and those ensembles can go to judges, and the code can be written eagerly, but then run intelligently and kind of scheduled and parallelized. So I'll skip forward, and I'll just note, as we go into the next section, this framework was called an inference time scaling architecture framework, not an agents framework. And I'll actually controversially note, I actually think that the classical definition of agents needs to be brought back. I think that we're often conflating desiderata that we associate with useful agents with the definition of agents. I think memory and tool use are properties of a useful agent. They're not inherently properties of an agent. In the classical RL definition, an agent is defined in terms of this framework with an agent, an environment, and some concept of actions that the agent can make on the environment and rewards that the agent can receive. Via this lens, the work that even Adept AI was doing a few years ago with large action models, which were really just a single model, that was taking in observations and producing actions, that was an agent in a limited way, all the way up to these kind of compound systems with many, many calls or multi-agent systems. That notion of it being a compound system is orthogonal to the concept of an agent. I like this definition quite a bit, and I think the properties of useful agents like memory, the ability to use a myriad of tools, et cetera, I think those are desiderata that we want from a great agent. Those aren't necessarily part of the definition of an agent. So that's my point there. Okay, great. So with that, I think we're out of time for the lightning talks. So now we're going to proceed to a panel with myself, Ramin, Tren, Bill, and also Igor from Grok, who's so chief architect there. And so everyone, please come up and take your mics. Testing, testing. All right. So we're going to have a panel, and we're going to talk about infrastructure for AI agents. We've got a great panel of people working across the infrastructure stack who've done a lot of interesting work. And I think we're going to kind of start off our session, and we're going to try to hear from the panelists what they think is unique about this agentic era, and why it's even an interesting question in the first place to talk about infrastructure for AI agents. What's new? What about this regime is different? So maybe we'll go ahead and query a couple of the panelists and see what they think. We'll start with Igor.
Hello, can you hear me? Turn it on. Can you hear me?
Hello, can you guys hear me? Okay. So first of all, great privilege to be here with the distinguished panelists here. What's different about agentic AI from the infrastructure perspective? What we see agentic AI doing is, one, generating a lot more tokens than just non-agentic AI. It typically requires very long contexts. Think about coding agents, things like that. And what it also requires is very low latency and very low cost. Imagining you're kind of constantly querying the model, so you don't want to sit and wait 10 to 15 minutes for your deep research query at OpenAI to complete. You want to do this really quickly so you can actually get more results and then iterate again and again. I never got an intro to kind of give on Grok, so maybe I'll take like 1 minute. We kind of meet all these requirements as a hardware. Grok started as a software first, inference first hardware startup at about 2016. And our focus from that point on has been maniacally focused on inference. And the resultant of that has been an architecture that's vertically optimized, from custom silicon to custom networking to custom kind of software stack that allows us to run very low latencies, best of breed latencies, very low cost. And we've been able to do this. With a 10-year-old technology. So Bill kind of listed a number of requirements for agentic AI: high memory bandwidth, a lot of model parallelism capability. And we have actually built this system. We have it available now. It's kind of setting records on performance, and we're deploying it across the world. We have data centers here in the US, in Canada, in Europe, Middle East. About 1.8 million developers working on this. And really, we're kind of embracing all the requirements for agentic AI. Thanks.
If I may, I'm just going to add, it's also, what's also specific about the agentic AI infrastructure is that it's full spectrum, as I said, from edge to endpoint to cloud. And it comes actually with different requirements for the hardware. Like on laptop, you want to go as low power as possible because battery life is important. In cars, you want to go as low latency as possible because if your self-driving car detects a kid jumping on the road, you want to brake rather in nanoseconds than in seconds. And in data center, it's all about compute power, a lot of memory, a lot of memory bandwidth. And also, it's fully connected. All these devices are talking to each other. They actually can discover each other, either they're in the same vicinity or not. So those are the big differences with what we've seen with the internet boom and the cell phone app boom and so on.
Yeah, well, I think most of this has been said. I think there's unique needs in terms of quality, quantity, and system issues. I mean, it's going to be a lot more tokens because you're working through this hierarchy of agents. They're going each through chain of thought. The quality is going to need a lot more bandwidth, a lot lower latency than what we're used to, and also a lot of resilience. We typically will build these systems across many GPUs, and we have to have everything operating all the time. And then these agents are querying tools, and a lot of the tools involve making queries to data lakes of different kinds, databases of various kinds. And so you need to have storage integrated in these systems in a very seamless way for them to do that as well.
Yes, I just want to double click on inference. It feels like data becomes an old field, and inference is the engine to generate new field. And literally, I see a lot of people sort of like training small models on a local laptop while making a lot of external API calls with bigger models to try to get these world functions. So it feels like there might be an economic shift from used to be doing research is like the cost of labeling data plus cost of training. Now it's the cost of calling inference API for model verification plus fine tuning. So that's a lot of opportunity for inference.
Yeah. Maybe a couple of things that I'll add. I'm both moderator and panelist, so I'll throw in some. Yeah. Very unfair, exactly. Yeah, maybe, and one thing I'll add is, I think there's a pretty unique distinction. There's kind of almost two regimes within agentic infrastructure. One is the very low latency, very performance sensitive regime, right, where you're asking a question and you're bottlenecked by a long agentic graph unfolding, and so you want each step to be as efficient as possible, and you care about latency most. And then there's also to a more extreme degree than I think has been typical, at least in AI, that async batch offline regime, where you might want to, for example, send off a query that runs throughout the night. Maybe you have a codex agent or something that's doing work for you asynchronously and just checking your code base when you're not working on it and can run overnight. Maybe you're spinning up many of these. And so it's actually this kind of unique, kind of two different regimes, almost probably kind of two phases. And building infrastructure that handles both well, or kind of splitting work across them, doing kind of indexing work, but then also serving work. I think that's in some ways a classic problem, but I think it looks a bit new in this new context. Okay, very, very interesting. So maybe on that point, actually, the next question is about what are some of the things that are stable in time that aren't changing? In what ways is history rhyming in this agentic infrastructure? I think, obviously we've been through a lot of phases of computing. Yeah, I'm curious what people think. Maybe we'll start from this side this time.
Okay, so because Lambda is like cloud, so I think operational efficiency is very important. We'll stay here for a long time. Just imagine a world where AI is going to consume most of the compute. And it's very important to effectively distribute those compute for different use cases, training, inference, agentic applications, and also making sure whoever has a compute can basically use them very efficiently. It reminds me about like early days of cloud computing. You have like virtualization is a great breakthrough. I guess the technique will change, the use case will change, but underlying principle of elastic provisioning, load balancing, those things will stay for a long time.
Yeah. Well, I think what people really care about is that they have a problem to solve, that they can solve it quickly and adapt quickly as their customers' needs change. And to me, there are two ingredients to this that I guess things have always been pretty consistent. One is programmability. You need to have a good, solid programming language that things are built on top of, like CUDA. And then you want to have frameworks and libraries so that when you want to prototype something, you're not starting from scratch. You can take something that's mostly there and kind of customize it and plug it together and get your solution very quickly. And I think that's something that's been persistent across many generations of technology.
I think in general, something that's consistent with each era is that the battle is won basically on three axes. One is TCO, total cost of ownership. It includes efficiency and all that. One is dependability, which includes safety, security, reliability, and so on. And the other one is user experience, as Bill was saying. And those are the same axes, but at each evolution of technology, the means to get there are different. For example, cooling, liquid cooling, and chipletization, for example, is one way to get to cheaper cost and better TCO. And open source software improves both TCO and user experience and so on. But the axes are basically the same as during the previous few technology booms.
Yeah, I agree with Bill. I think user experience is going to be key. How quickly can you deploy your workloads onto the hardware? So that's key. I think the other piece is really efficiency. As we know that power performance area is really important for CPUs and so on, but as you scale hardware at a much massive scale, this is going to become even more critical. So just like we've optimized mobile processors so our batteries last a long time, I think we're going to be driving that level of efficiency on inference hardware because we're just going to be generating so many tokens, so many calculations need to be made. So that's kind of key.
Yeah, very interesting points. Yeah, I think the one thing that's becoming clear here in your answers is there's always a question of, is this time different, or are some problems classic and repeating? And I think there was a period, probably even just a year ago, when in AI the broad consensus was that we would just do kind of pre-training, scaling. That was going to be the only regime, and then we'd be inferencing these kind of monoliths. And that would be it. I think it's becoming clear that now there is going to be a heterogeneity of workloads, a great variegation of workloads, different types of training workloads, post-training, pre-training, inference-time scaling, types of training, et cetera, and then also very different types of inference workloads with different SLA profiles, et cetera. And that's a classic problem that systems people have been wrangling with for a long time. So interesting to hear that this time is not different in some ways, while being very different in others. Yeah, going forward to another question, I guess the next question, maybe two questions in one, take it as you will. One is, what are things that the consensus is getting wrong? Ideas and perspectives and opinions you hear a lot from colleagues in the industry, from Wall Street, or the media, et cetera, that you think are misguided. What are problems that are getting too much attention, problems that aren't getting enough attention, that kind of, what are people wrong about? Where do you have a different perspective that's a bit divergent? Maybe we'll start inside out this time, Ramin.
Okay. So to be maybe a little contrarian, the fact that the new compute is now only GPUs and CPUs are dead, CPUs are actually re-emerging. So GPUs definitely are exploding, but they're making actually CPUs re-emerge, especially with agentic AI calling tools. Those tools are mostly on CPUs. The other thing is what you mentioned about pre-training. Actually, the explosive era of pre-training is probably slowing down, and we're running out of data anyways for text, for video images, it's another story. But what is really scaling right now is post-training, especially with RL for verifiable domain, as well as inference with generative inference, which obviously generates an awful lot of token with tree of thought and so on.
Igor.
Yeah, so I think one of the biggest misconceptions that I find is that the belief that what the infrastructure that got us to this point is the same infrastructure that's going to take us forward. So if you look at most of the focus up until now has been training, and we've built really good training hardware. GPUs are unbeatable on this, and they're going to continue to do really, really well. Inference is a whole different beast, right? You're not processing high batch. You're not running it once. Like if you look at the hardware needed for inference, it's about 20x than the hardware needed for training. So the efficiency of that hardware needs to be significantly better. The latencies, as I mentioned earlier, need to be better. Real-time processing is key. And this is very different hardware. So I think thinking that we're just going to scale more GPUs for inference, I don't think that's going to happen going forward. I think it's going to be a very unique custom designs that need to be brought up.
What do you think about that, Bill?
Yeah, so GPUs today are the most efficient and most commonplace platform for inference. They do a really, really good and really efficient job of inference, and they've been optimized for that. We actually optimize for distinct workloads. We do optimize for training. We also optimize for inference, and I think going forward, they're going to be quite good at that. I think the one big sort of error in conventional wisdom that I see is not using GPUs for inference. It's focus on large models, and I sort of understand why people do it. Everybody's worried about their flagship model, but especially as we move to agentic systems, what I see happening is people distilling the really big models into smaller models that are then specialized for their particular task in the agentic system. And I think there's going to be much more concern with running an 8 billion or even a 1 billion parameter model really efficiently than running some behemoth trillion parameter model, especially as we move toward mixture of experts. And this is actually one way of doing mixture of experts, kind of at the level of individual agents. You have agents with just the knowledge they need.
Very insightful. Yeah. Sean.
And so just to get myself out of the debate here, I'm going to talk about eval. So I think eval is something both over-indexed and underutilized. The problem here is the disconnection between leaderboard eval with the real-world problem at your hand. Again, I'm going to make a connection between eval and recruiting. Just imagine, like you are looking at someone's resume. What the person did at school in terms of course and scores are sort of important in the early stage of career, but it gradually become irrelevant. What I really care about is what they did in the past in terms of project, what they built, and how that is going to help you with your task at hand. So really, it's going to be embody the eval and the continuous development.
Case in point, Llama 4 was #1 at all the evals.
Yeah.
All right, I'm going to dodge that. Awesome. Yeah, it's very interesting. Yeah, I like a lot of these points here. Bill, I think your point's particularly thought-provoking. Yeah, among several things, I think one of the misconceptions that I'd like to combat a little bit is the idea that basic research is dead, that it's all engineering from here on out, that we've answered all the questions, we just need to scale things up. Yeah, claps for basic research. All right, awesome. Yeah, a couple of claps there. Yeah, I think that as one case study, the recent Gemini DeepThink model gets kind of a greater lift from parallel thinking than it seems like some other models have gotten. And I think there's a lot of evidence that composing these models, you can get kind of much better results. And so you've started to see academic labs doing work at this kind of inference level of the hierarchy. And I think there's a lot of gains to be had there. Like the differences in the way that you construct these ensembles, the type of aggregation functions, it can make a big difference. And so I think we're going to start to see, hopefully, the pendulum swing back. And there'll be a lot of room for novel research ideas, just like in the kind of 2010s and neural networks here. So I'd encourage people to, kind of aim for the frontier. Awesome. Okay, so with that, actually, that's a nice segue to a last question here. We have like 3 minutes or so left. I'd love to talk to the panelists about what is your advice for graduate students, researchers, and people in the audience who are trying to push on the frontier, who kind of want to make things better, even at either at the infrastructure level, at the applications level, or kind of the models level. Any advice for people? Maybe starting with Bill.
Yeah, so my advice is to reject conventional wisdom and try to think about how good things could be. Try to come up with a physical argument for bounding what level of performance you could achieve, what results you could get, whether it's out of an agentic system or a piece of hardware. And then start from first principles and look at that. Too many people are kind of doing incremental things, taking the conventional wisdom and trying to push it another notch forward. And the real big leaps happen when somebody tosses that aside and starts from first principles and says, well, here's how good it could be, and then pursues that.
Chun.
Work on small models, try to make them big models. It's just very cool in multiple ways.
Ramin.
My advice is be a full stack scientist or engineer, meaning it's good to specialize in something. Like if you want to specialize in AI architecture, that's great. But be full stack. Understand the hardware. Understand the communication issues. Understand the model. Understand the application level. Because that's what I've seen throughout my career. The best outstanding engineers are full stack engineers. They're never people who know everything about one thing. They're people who know nothing about everything.
Very interesting. Igor.
Yeah, I'm going to echo Ramin's comments there. Yeah, I like foundational science, focus on that. I like breadth of understanding. I think this is a big challenge also. If you look at our infrastructure, everybody's focused on the chip, but nobody has looked at how do you deliver power? What's the loss of that power delivered? How do you thermally cool these things? How do you pack racks? And that is really maybe less sexy than kind of getting tops per watt out of a chip, but it is super important in our data center. So just this broad understanding of how the whole stack is built, and maybe you can then focus on it in depth on a component, but just get your broad understanding of how everything clicks together.
Yeah, I'll actually have to third that opinion. Yeah, I think driving a nail through, focusing vertically is really important. Kind of not constructing arbitrary boundaries around what is in your domain versus not. I don't think people appreciate the extent to which infrastructure has shaped research, the extent to which the transformer co-evolved with the TPU pod. And isn't really necessarily a smart thing to do versus the LSTM, but it makes a lot of sense if kind of memory bandwidth is a constraint and compute is very, very you have dense computation systems. So, yeah.
And if I may, just to give a concrete example, the reason I say the most outstanding engineers are full stack is because they're the only one who can debug a problem. Because when there is a problem, you don't know if it's in the model, it's in the software, it's in the hardware, it's in the communication. And if you're specialized in one thing, you just won't understand the problem. People who are full stack, whether it's software, hardware, model, communication, anything, they just figure it out.
Yeah, really, really great point to end on. Thanks for a very, very fun panel. I learned a lot. Thanks, everyone.
Thank you. Thank you.
In the session 2, we are going to have a session for frameworks and stacks for agentic systems. My name is Chi, and I'm the session chair. I'm also one of the speakers. So let me introduce our keynote speaker first. We'll have Jan Stonica, co-founder and for Databricks and Anyscale, also a professor at UC Berkeley. After the keynote, we'll have 6 speakers. Matej Zaharia, co-founder and CTO from Databricks, also associate professor from UC Berkeley. Sherwin Wu, head of engineering, OpenAI API from OpenAI. Myself, Chi Wang, senior staff research scientist from Google DeepMind. Jerry Liu, co-founder and CEO from Llama Index. Matt White, director, general manager of AI from PyTorch and Linux Foundation. And last one, Brad Axon, tech lead of AI and data platform from Block. Okay, and after all the speakers, I will have a panel. We'll have a panel with all the speakers, and I will moderate the panel. Okay, I'm looking forward to the session. Please welcome our keynote speaker, Yang. Thank you.
Good morning, everyone. It's a real pleasure to be here, and today I am going to talk about reliability in the context of AI, and this is a theme which is present in many of the talks you are going to hear today, but I just wanted to emphasize a bit on this aspect. So what is reliability? This is a definition according to the NIST, the ability of a system or component to function under stated condition for a specified period of time. And the reliability encompasses many things, has many kind of properties, like accuracy and correctness, consistency, predictability, robustness in the presence of unexpected inputs, and safety. And now, you heard this quite a bit, and I just want to, again, to emphasize that reliability is actually a critical aspect of the AI success. It's like without building reliable AI systems, it's hard to imagine how AI will have the impact everyone here hopes is going to have. And there have been many papers, academic papers, thought leaders like Dario Amodei always speaks about the importance of building reliable AI systems, AI agentic systems, and also obviously you have a lot of blogs across industry talking about the same things, okay? So now, it's the reliability, it's actually, you have that it's a key property of any kind of engineering system, including software engineering, software systems. And why is that hard? Why is it challenging? Again, you can look, at software systems, and we know there, over the 40 years experience or more, 50, well, more than that, 60, 70, is that building a feature, it's actually demonstrating it, prototyping a feature, it's actually quite easy. However, to productize it, it's much, much more difficult. It takes anywhere between 10 and 50 times more effort to productize a feature than prototyping and demoing it, right? And the main goal, actually, of productizing a feature is to make that feature or to make that system reliable, okay? To work as intended. And productizing a feature includes many things, like obviously testing and debugging, right? This is what you do to put the feature in production. You really need to do that. Compliance, governance, and when you deploy it, you need to have observability and so forth. In this talk, I am going to mostly focus on the first bullet, testing and debugging. And how do you do that in software systems? Well, software systems consist of many components. Think about function, object, actors, tasks, subsystems, and things like that. And each of these components ideally has a clear specification, an interface, okay, which describes what are the expected outputs given the inputs. Also may describe what are the allowed inputs and many other things. And this is important because this allows us to write tests, which verifies that, for this input, I get the expected outputs. And this is fundamentally what allows us to test and debug the systems, right? You write this test, you see that test pass, and if they don't pass, this is how you are going to identify the component which fails, right? And in the components, then you go, subcomponent and so forth, down to the line of code which violates this, doesn't function according to specification. And you fix the problem by changing the offending code and then rerun it, and hopefully you are going to pass all the tests, right? This is what you do iteratively, okay? Now, the problem is that debugging AI agents, at least from this aspect, is much harder. If you think about, we are talking about agentic systems. One of the key components of agentic systems is large language models. And you rarely have clear specifications. And therefore, if you don't have clear specification, it's even hard to know when an error, if an error even occurs, right? It's also there a black box. So even if you know the error, how you are going to fix it, and by black box meaning here is that I'm contrasting with a program or it's kind of white box because you can go down and identify maybe down to the line which has a problem. But here it's like almost it's like debugging. If you use that analogy, you have a program and you only can look at the outputs, and based on the outputs, you have to figure out what happens. Okay. So now that I kind of provide the framework, I'm going to talk about two projects. And one is Chatbot Arena, which is testing and evaluating large language models. And MAST, a new project done with a few of my colleagues and students here. And you are going to hear a little bit more about it later in the day, which is a taxonomy for errors in multi-agent systems. LM Arena was previously Chatbot Arena. It's a human evaluation for large language models. Why do we care about it? We have a lot of benchmarks out there, right? And every day you have new benchmarks. It's because most successful AI applications, at least today, have the human in the loop, right? If you think about chatbots, right? Customer service. If you think about code assistants, they do have a human in the loop, okay? And therefore, you want to know how and to evaluate how these systems, how these large language models perform with real people, with real-world prompts, workloads, and hopefully in real time. So, and when you are going to have humans interacting with these systems, the one central element is kind of the human preference, right? And the human preference is kind of not very well defined, but without trying to define it more, I would say that it has two components, what we call substance and style. The substance is what you say, accuracy, factuality, right? Is a result correct? Right? It has the right information. But the other one is style. How the output look like, right? And it's kind of, it sounds much more superficial, right? But I want to make the point here, but it's also extremely important. And we know that, right? Presentation, we are going to give presentation. You know, bad presentations versus good presentations, the content can be the same, right? But obviously, a good presentation, you appreciate it. And why you appreciate it? Because you are going to get much more from a good presentation, from a bad presentation of the same content. But look further, everyone is using computers, right? Arguably, a computer which just has this kind of alphanumeric character, screen, can provide you the same information, right, as a window-based computers, right? But why we do prefer the window-based computers? Because we can do our work better. So in fact, the style determines how also reliably humans interact with systems, right? And it's not only in computer systems, it's everywhere. Designing cars, appliances, everywhere, right? Because a good, we call this UI UX, right? It helps people to be much more effective in ingesting, retaining, and processing the information. And this leads to reliability of how they interact with these systems. Okay? Okay. So what is LLM Arena? Probably everyone now knows by now. It's like you go, and I encourage you to go to the site. You can ask questions, and then you can get, like in this case, what is AI reliability? And then you are going to get answers for two anonymized and randomized large language models, And then you can pick which one is better, if you want. And all these votes, we just use to compute a leaderboard, actually to compute this rating in the leaderboard using Bradley-Terry model. And this is a general rating, but you also have rating on categories, different categories like coding, multi-turn, and so forth, hard prompts. And also we don't have only for text, but also for multi-modals, multitask evaluations, like obviously web development, search, vision, and so forth. In fact, this week we launched this kind of video arena, which is text to video and picture to video. And I have only demo in the stock here. And here the question is about, this is like the web page for this event. And I just want to animate it and show the Golden Gate Bridge appearing in the background. And I think on the back, someone has to help me here because I don't have. So if you can click. OK, so if you play the one on the left. OK, so this is one result. And one on the right, please. Whatever. OK, so now you can vote which one is better. And if you want to have more fun, exactly. So you can go on Discord and play with it. OK? Now we are talking about the style, right? So the question, OK, you have form, style, and so forth, substance and style. And it's always a question we are always asked, does the styles matter? And how much? And we have some kind of, we did have some analysis on this. This is last year, and this is also this year a new blog. It's, I think, very recently in April this year. The sentiment, it's kind of, the style here, what means is mostly the format of the output. The sentiment, it's also kind of the vibe, how the language. Is the answer positive or positively framed, negatively framed, has emoji in it, things like that. And here are just kind of results in terms of the correlation. This is basically some linear regression we run on the data we have. And if you look here about the length of the text, the answer, then the markdown, right? The formatting, right? You have a list nicely formatted, you header, bold, what is important in the answer. The highest impact, if you look at all of them, it's a length. And one of the reasons the length, the longer answers are preferred because typically also they have more details, okay? If you factor out the length, then the next one will be the markdown list, which you kind of expect is more kind of structured. So it's more important than the header and maybe and so forth. And if you look now in the most recent study, again, where we have also, this very negative, neutral, positive is kind of the vibe on the answers and so forth. Again, the answer length remains the dominant factor in impacting the answer, the preference of the users. But the one point I want to make, because there are a lot of things, written in, over X and net and so forth, emoji, right? People say, oh, it's like it's easy to fool, not they say to fool, but which is the wrong word to start with. You can get, better if you have more emojis. And actually, it's not. It's actually, it has the number of emojis, the emoji count has a negative correlation, okay? Maybe this is something about the audience of Chatbot Arena, but this is what the result. So LM Arena had a big impact, has certainly much more than we ever dreamed. Now it has 3 million monthly users, over 10 million monthly conversation, over 1 million monthly votes we just reached this past 30 days. And we've seen over 700 models from 20 providers, model providers, and yeah. Yeah, thank you. Okay, So this was about the LM arena, and again, what I want you to take away is that actually the style is very, very important, right? And paying attention to the styles is something you should do when you build these systems, because it's equivalent of paying attention to the UI, UX on building traditional systems. The next talk I'm going the next part of the talk is about multi-agent system failures and taxonomy. So this is Agentic Summit. We are talking about agents, and there are many, many agents up there. So now questions in the context of my talk is about how reliable they are. And at least when we tried, the past 1-2 months and so forth with the data we have, many of these agents fails more than 50% on hard benchmarks. Right? So here it's the success is blue for different agentic frameworks. The failures, it's orange. Okay? So the obvious question next is that why do multi-agent systems fail? Right? So the goal of this project is to systematically identify, classify, and analyze the reasons why these multi-agentic systems fail. Right? And I'm going to go pretty quickly over the next slide because I want to get to the end, because I have to say also something at the end. So how do we do it? We manually inspected students, here I have Melissa, Mert, inspected over 150 traces to build the failure taxonomies. Based on their data and their learning, they design a LLM judge pipeline to evaluate over 1,000 more traces. Right? And it's a data set which is public. And we have 95% agreement between this pipeline and the human evaluation labeling. And again, we open source both the data set and the taxonomy. And we look at a bunch of frameworks. Okay? And what we came out with this taxonomy, and basically you have whatever bins here, you have specification issues, inter-agent misalignment issues, and verification issues. And the one point to take again, I am not going to go through all of them, obviously, I don't have time. But if you look on the right-hand side of the percentages, each of this kind of category is significant, okay? So the first is specification issues. So specification issues, it's like there are everything about not understanding or disobeying the specifications, disobeying not only the task specification, but your role in many of these agentic systems. You say, each different agents, they have different roles. They do repetition, right, without making progress. There is loss in translation or some conversation information loss and so forth. And here it's, like for instance, in this case, you have this kind of in chat dev, is basically you are going to build the system, you have a CEO, you have a CPO, and the software engineer and the tester and so forth, and they try to cooperate to implement a task. And in this particular case, the CEO starts by telling to the CPU the kind of what that the CEO wants from the CPO, but the CPO kind of stops the conversation, right? It's again like and you'll see you heard a lot about these things. I think Jared early on. This is not about a limitation of LLMs, but also about how these agentic systems are designed, right? So, and there are many, many examples here that if you have a better design, you can improve the accuracy and for the particular task, even keeping the same models, right? The next category is inter-agent misalignments. These are, conversation also reset is like, fundamentally, a lot of these things are kind of lost in translation, right? It's like you say something, the other agent doesn't understand or makes things up or things like that. And here it's a very simple example. And I'm going to go quickly because I don't have time to go step by step, but I'm going to tell you what it's doing and what is the problem, okay? I'll give you that. So what you have here, basically you have a supervisor agent asking a phone agent to send a WhatsApp chat message, okay? And but the first thing you need to do, you need to log in the WhatsApp. So therefore, you send the username and the mail and yeah, that will be a few more minutes. Yeah, and what happens here, you send the information to the phone agent, and the Python executor asks eventually for here is for the username and kind of the password, okay? And suffices to say that what happens here is that in order to provide to the executor, the Python executor, which eventually has to log in and to send him the message, the phone number, you provide the email address, right? That's a kind of the confusion what happens on the phone agent perspective, from that perspective. But more than that, the error which is returned to the supervisor agent doesn't say anything about that. So you cannot fix, you don't know what is the problem, right? So something happens, was lost in translation, kind of was confused. The phone agent, instead of giving the phone number, gives kind of the email address. And this error was not sent back to the supervisor, that detail, so the supervisor agent cannot fix the error, right? Okay, and the last one, so basically here you need real deeper social reasoning, meaning that what are the gaps in the understanding, in the specifications, and you need to fill them. The agent has to have that kind of knowledge. And the final one is task verification. Everyone knows about task. We are talking about the unit test and so forth. And here there are all these agentic framework, they do have some verification, some agent verifier. The problem is that they are quite weak. And even in simple things, like here it's about designing a chess. And it's like there are millions probably of chess programs on the web. And you've also asked to use a standard notation. So there are two things here. First of all, the agent fails to do it. You have things like pawns can move backwards instead of the notation like queen f7, they put x and y. That's okay. But the verifier, it says the program is good. Okay? So, so really here we can do much more. Okay? So I'm not going to go here. I'm just going to tell you. Each line of this is for chat dev. Each column is for chat dev, and represent different categories of failures. And in each category you have subcategories. Again, the point to take away is pretty diverse set of failures. And this is for all this kind of agentic framework we look at. It's very diverse. But again, each of these kind of bars is significant, at least a few percent. Okay? And here we just launched, was today, about annotator web. So you can go there if you have your agentic framework and you are going to have your tasks, and you can upload here your traces, and we are going to use our pipeline to label the failures in your traces, and we are going to make it public and share with the community. So again, it's kind of. So in summary, I'll take only 2 more minutes, okay? So reliability is critical to the success of AI, okay? And there are 2 aspects of reliability we discuss in this. I discuss in this talk. One is about LM Arena, which is understanding human preferences, which is key to effective and reliable interaction with AI systems, and the MAST, which is trying to understand why multi-agent systems fail. Of course, you need to understand why they fail in order to fix them. And obviously, this is just a starting and many challenges to address. Probably 60, 70% or more from this room are working on these kind of challenges. So some parting thoughts here. Reliability, like we discussed, is important in every system we rely on. Okay? Period. Cars, appliances, everything. So it's a staple of the engineering disciplines, right? And reliability in AI arguably is more difficult than other systems. And one key here, which you have in this, how we get to the root of trying to build reliable systems in other disciplines, is to have good specifications for entire system, subcomponents, and things like that. because these specifications allow us to verify the system works. If you don't know the specification, you don't know what the system has to do, what you are going to verify, right? So verification implies that you have some kind of specification. It also helps you to debug the system because especially, it's like because you have different components, you can end-to-end, it doesn't work, then each component, this component doesn't work, you go more in depth and so forth until you find the cause. Maybe you just replace the component, right? This is what we do with everything, right? It also allows you to decompose and reuse existing components. Right? Why? Because the components have a clear specification. Now you know how to plug them in. This is what we do in software engineering. This is kind of the exponential growth we have seen for the past, 40 years. And finally, today we have the human in the loop. But one of the reasons of the human in the loop, because the human is the ultimate decider about whether the output from that system is good or not. Right? That's what you do in code assistance when you use cursor. You are the ultimate arbiter, right? Decider to say, this looks good and I'm going to approve this kind of changes, right? If you want to go to automated decision making, which means no human in the loop, you need to trust this decision without the humans overseeing them, right? And you cannot trust them if you don't know exactly what that system is supposed to do, which means without having the specifications. And I think that basically, again, it's like, I think we should learn, obviously, from other disciplines on how to build these reliable systems. And a few of us, which are many here, like Matej and others, we are very excited about this research direction. Thank you.
Okay, hi everyone. I'm Matej. I'm one of the speakers giving shorter talks here. I'll be talking about some research we've been doing very recently in our group at Berkeley with some collaborators from Databricks, Stanford, other places as well, on what we call reflective optimization of agents. And this is part of the DSPy open source project that my student Omar started, and that we're actually contributing this work to. So the big question we're looking at is how can we teach AI new tasks? Everyone is here, like 12,000 people or whatever, because AI is promising, but it doesn't quite do what we want it to do. If it just did what we wanted to do, we wouldn't come out on a Saturday, to a conference about it. So obviously, it's important to be able to teach it to do the new things we're trying to build in our application. Now, traditionally, the way this was done in machine learning is through weight updates. You've got these large models with lots of parameters, and you use calculus, you use gradient descent, and if you set up the right sort of objective and loss function, you do weight updates and you train your model. And this is everything from pre-training, where you predict the next token, to supervised fine-tuning, to reinforcement learning with verified rewards, which is the latest things we've been using for math and coding. So it works really well. We've been able to teach a lot of things, but it requires huge numbers of examples, and that's what makes it hard for, like, say, everyone in this room to pre-train their own model, for example. It's literally trillions of tokens you have to practice predicting to pre-train a model. It's hundreds of thousands of rollouts for RLVR, if you look at any paper that does that, and for supervised fine-tuning, it's tens of thousands of high-quality examples where, like, someone spelled out what you should say. So one of the things happening is, as we saw in the earlier session on hardware and infrastructure, actually flops are getting cheaper, training algorithms are getting better. So actually this kind of training is going to get cheaper. But the thing that's not getting cheaper is if your task is slow to get a reward from, to run an example and get something from. Like, for example, scientific tasks where you have to run an experiment or something like that. You can't run 100,000 experiments to teach a model something, regardless how cheap the GPUs are and the data centers and all that. So actually, I think that for many capabilities we care about, progress in them is going to be limited by the sample efficiency of our machine learning methods. So we need to reduce the number of samples required. Okay, so how can we teach models more effectively? What is there to do? Because we've seen gradient descent work so well. Let's look at reinforcement learning as an example with these verifiable rewards. We got this big model. We give it some tasks to do, like solve a coding problem. Maybe we give it tools. it might write code, it might search the web, it might use a debugger, whatever it does. So it does all these sessions, imagine like an agent for something like SweBench. It's doing all these trajectories trying to solve the problem. And then at the end, we just check, did it solve it? And we give it a 0 or a 1 based on when it did. And then we pass this through our loss function, and we do gradient descent on all those weights. So there's so much that happened in these trajectories that maybe is informative, like why did it fail? It got this compiler error message, or like it ran out of time or something like that. But all we get is the 0 and 1, and then we ask, oh, can we take a derivative with that and see how to update the weights? So basically, we've lost a lot of information. And imagine, these rollouts can take minutes, but imagine you're using your model to, where it has to like do an experiment or something in the physical world. These could take hours, and we just condense them down to a 0 or 1. So the idea we're exploring is what we call reflective optimization, and we do it in prompt space. So there's two pieces to that. One is, instead of only using this 0-1 signal, we actually ask a language model to look at the whole trajectory. Look at what you did. You ran this command, you got this output, you got this message, blah, 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 and reflect on what happened. So potentially integrate all this information to figure out what went wrong. And then instead of using that to update some weights, which is hard to do with like a natural language insight that the model might have had, we use it to update a prompt. Basically, we tell it, write down some notes for yourself for the next time you do this task so that you can do better. And the great thing for that in terms of sample efficiency is even from one sample where you make a mistake, you might write an update to the prompt that like completely avoids that mistake in the future, which is not really possible if you make a small change to your weights. So this is what we're doing in this project called JEPA, Genetic Burrito. It's basically an evolutionary algorithm for prompts that combines these ideas. Also related to AlphaEvolve, if you've seen that, which is a genetic algorithm for writing programs. So how does it do? I'll show you some examples where we compare it with other things. So this is an example where you teach a model to do multi-hop search and question answering on this benchmark called Hotpot QA. And we compared it with GRPO, which is the premier way to do reinforcement learning with verified rewards. And you can see we ran GRPO up to 25,000 rollouts. Actually, people run it for hundreds of thousands for this, but it's getting better, but very slowly. And then we ran JEPA and Blue and MIPO, which is an older prompt optimizer. It's also part of DSPy. And these learn the task a lot faster. Even in like a few tens of rollouts, they're actually higher than GRPO is going to get in 25,000 rollouts or experiments. So they learn it quite a bit faster. They actually also outperform the numbers where we stopped running them are higher than what you get in papers that specialize models for this, like Search R1 or Zero Search. So definitely they learn a lot in a short time. What are they actually learning? This is the cool part for me. So this is sort of the original prompt. Hotpot QA is something where you do multiple steps of questions. So for each step, you got your results from before, and you generate a new question. So there's the original prompt, which is very simple. Like you got your first summary, and now you generate a new query. And then there's the new prompt, and this was completely written. This one's from GPT 4.1 mini, but the Quen one is similar, just by the model reflecting on its past mistakes across a few hundred steps. And it's a very detailed prompt. It has some examples. It tells it pitfalls. Unfortunately, I have a short talk, so I can't read the whole thing for you, but you can find it in our paper. It's very quick to build this up, and it actually greatly improves performance on these tasks. The same thing is seen across other tasks. This is a claim verification one. So MIPO, the green, was our previous prompt optimizer, so we also had to beat that. It would have been underwhelming if we didn't. So we do better than that, but definitely both do better than GRPO on this. This is also multi-hop search for claim verification. Some other fun ones, you can apply this to closed source models. So you can, even if you can't fine tune them, you can actually apply this. So we tried this on math. There's this live bench for math, which is like recent math problems with GPT 4.1. And GPT 4.1 is also the model that reflects and updates the prompts here. There's no cheating, no distilling by having a very powerful model write your prompt. And you can see JEPA, I think this is about 2,000 steps, ends up making GPT 4.1 do better than the full GPT 4.1. And this is the prompt it writes. And it's like, I mean, this is not the prompt I would have written, but basically it's tailored to the kinds of mistakes that this specific model makes that were found through this genetic algorithm to do better across lots of samples. We also did this, we also did this for coding. We have this new hardware accelerator from AMD that does pretty much no resource for on the web, and we were able to outperform human-written agentic plus RAG pipelines for this, and we're doing it for other tasks as well. So that's JEPA. I think it's a class of new optimizers that is going to be very powerful because as language models get better, they should get better at reflecting and at following instructions. So maybe the weight updates of the future are going to be prompt updates that use the full capability of these models. It's part of our DSPy open source framework, which is, it's a framework where you can just declare an AI workflow and will optimize the prompts and even tune models for you based on a training set to do as well as possible. And a bunch of other optimizers are also in there already if you want to try them out. Lots of users are doing that. So that's something that I'm very excited about, and it could be the way that we train AI in the future, and we'd love to try it on your tasks. If you have a task, reach out to us. These are all the folks on the paper. Thanks.
All right. Hi, everyone. My name is Sherwin. I work at OpenAI, leading the team that works on the OpenAI API, which hopefully some of you have used. And today I wanted to give a brief talk on what I view as a retrospective on an early retrospective on the year of agents. This is going to be a pretty fast talk, so I know we're running behind on time, so I know the organizers will appreciate that. So I've been working on the API for quite a while, pre-ChatGPT era, back when the main use cases of these LLMs were just copywriting startups and role play like AI Dungeon type companies, and it's been crazy to see the progress of these things. And now that we're in 2025, it's been really awesome to see the paradigm of agents and reasoning kind of come into fruition. So much so that there are conferences now completely around AI agents. And we were told, in early 2025, I think Sam was the person who would say this a lot, but we were told that this would be the year of agents. And I think part of this was, I think a lot of the labs, a lot of the companies started seeing the impact of the new reasoning paradigm on how long these LLMs could reason in a consistent and reliable, more reliable manner, still not completely reliable, and extrapolating that into something that could resemble agentic behavior. And so because of this, at OpenAI, we've tried to launch a lot of different products kind of in this vein. So in January, which feels like forever ago, we launched the operator model with a computer using agent. In February, we launched deep research. Crazy to think it was only 5 months ago. In March, we launched Responses API, which allows developers to build more agentic-like behaviors. April had the launch of O3, which is this, it had access to a lot more tools. It could do research. It could run code for you. In May, we launched Codex, which was a coding agent. And then last month, we launched ChatGPT Agent, which merged a lot of these together. And then, who knows what will happen in August. Still have 31 more days, or I think 29 more days. But if you kind of look back on all of this, these are really cool demos. A lot of people actually use these in their day-to-day. But now that we're halfway through 2025, personally, I still don't think agents have really lived up to their promise. And I think it still hasn't really hit the mainstream. Certain use cases, certain more generic use cases tend to have agents that work, like maybe for deep research. We're now starting to tailor them towards domains like coding. But it feels like they really haven't hit the mainstream yet. My day-to-day work doesn't really feel that different with agents. And so it brings back, it makes me think about this really great book called Where's My Flying Car, which in the 50s, 60s, we had all this optimism around flying cars, and they still don't exist. I think I saw a startup try to do this, so maybe soon. But the equivalent here is, where's my agent 6 months in? And and so one way of thinking about this is, what are not the reasons for why agents aren't here? So I'll first cover this, and then I wanted to cover some reasons why I do think agents are still not really prevalent yet. I think there are two things that it's not. So one of them is definitely not a lack of demand. I've heard people think like, oh, who wants agents, you know? But what we've seen over the last year is the moment an AI agent starts working, the usage just absolutely explodes. So I think deep research was a good example of this. I think we're seeing this right now with the coding agents, with Cursor, Claude Code as well. But the moment, you know, we're all kind of, we all care about our own time. And so the moment an agent can kind of save us time, everyone starts using it. And so the demand really is there. Second thing is and this might be a hot take, is I don't think it's due to a lack of model intelligence anymore. These models can start getting really, really smart. I actually think O3 is at a level that even exceeds myself a lot of the times. And a fine-tuned version of O3 deep research is straight up better than me at researching complex tasks. Like I'm not that diligent. I will not synthesize things as well as deep research. And so I actually think it no longer is limited due to a lack of model intelligence. And so something we talk about internally is the capability overhang is very real right now, which is why it's a very exciting time. These models can actually do a lot of these things, but for a variety of other non-intelligence reasons, the agents still aren't really there yet. And so, so my main take here is that I actually think the primary reasons why agents aren't everywhere yet is actually deployment related and not not intelligence related with these models. And I think there are four main things that are still blocking agents here today, which actually to me I think is really exciting and is an opportunity. The first one is connectors. So we still haven't built out the ecosystem of tools and connections for AI agents to actually get info from the world around it to be useful. I think we're starting to do this. You're starting to see a lot, but we're still not fully there. Second thing is a lack of generalizability. I actually think the previous talk kind of touched on this too, where these models still, you can train these models to get really good at very specific tools, but once you generalize beyond that set, they start having issues. Third one is it's still really hard to create agents. I talk to customers of our API about this all the time, and because it's so difficult, because there's so much activation energy, I think there's a lot of workflows in the world that still haven't really been touched by AI, and if we can make this easier, it'll drastically improve that. And the last one, which I think the previous session talked about, is cost. So these things are still not, Sam was talking about intelligence too cheap to meter. These are still meterable, and if anyone's run a large Claude Code job or a Cursor job, you know that this it hits your wallet quite a bit. And so the cost is still a prohibitive factor. And so for the first one, connectors. So yeah, the main point here is that the scaffolding that these models need to build to access the right data is still not built enough yet. Is still not built out enough yet. We're still in the early stages here. And the analogy that I have is the agents or the models right now kind of look like this person sitting at a desk with a computer with nothing else in their office. You can, you're kind of sitting there, you want to be helpful, but you don't have any access to any data. Maybe you could draw a fun picture for yourself, but there's not much interesting things that you can do. This kind of feels like the world that we're in. And the person themselves, presumably is very smart and can do things, but they don't actually have the infrastructure that they need to do it. We're starting to see standards evolve here, which is great, but they're still not fully mature yet. You kind of have seen these evolutions of, vector stores were really hot a couple of years ago. Then I think people started thinking about more simple search. This is how deep research came about. Now MCP is a really great new foundational paradigm, but it feels like we're still early, and there's still more to be built out here. Just to put it into perspective, MCP literally did not exist, I think, 8 months ago. And it is only now started really taking the industry by storm. If you just look at the star history of the different servers on the GitHub of MCP. And that's not even to say, MCP tends to target a lot of external use cases. Internal use cases, businesses, what we do in our organizations is even more daunting. Estimated, the amount of data that is stored in internal organizations for access is estimated to be 4x larger than even public data by end of year. And so if we're having trouble, connecting to public things at MCP, imagine how hard it'll be to start transforming the structure of the tools for your internal organization. The next thing, lack of generalizability. So agent tool use is still not very generalizable, unfortunately, and it results in agents that are trained on very specific tools. So the Kua agent was trained on like a click and like a browser tool. Our deep research is just trained on a thin search type of a tool. And so you end up getting these things that are trained with very general purpose tools like search so that you can get maximum broad utility. But once you go beyond that, it gets very difficult. If you've ever tried deep research, it's in our API. It's also a product, but if you use it in our API, you can actually give it random sets of tools, see how it does. Deep research is really great at using search. We fine-tune the hell out of it to get really good at search. If you give it other types of connectors on our ChatGPT product, it's okay. It's pretty good at it. It's actually really cool to give it GitHub and have it search through that. But if you start giving it custom tools of your own, connect to your Databricks cluster, connect to your Snowflake cluster, it starts having a lot of generalizability issues. There's a paper that our friends at Apple put together which kind of illustrates this in a more quantitative way. I'm not going to go through all of it, but basically, as you start perturbing the tools, giving it custom tools that it might not know about, the performance on eval start going down pretty precipitously. And so one big question then is, how do we create tools that help the model work better? A lot of the times, I think we've been thinking about how do we create things that make humans more valuable, but I think very soon we're going to be in a world where we're going to have to create tools specifically tailored for the model. And so this idea of like simple tools, simple standards, and a very smart model, I think the previous panel talked about a very small on-device model, just like reaching out to a lot of different tools. That really does seem like the way in which the world's going to go. The third one, difficulty of creating agents. So I'm going to put my own company on blast here. This is a PDF on a practical guide to building agents. It's 32 pages long. There's like all these diagrams of like the different architectures you want to do. It's still really hard to build agents right now. And I think for us to really unlock the long tail of things that agents can do, we're really, the long tail of economically valuable tasks, we're really going to need to make the agent creation process a lot easier. I think a lot of companies are thinking about this. Last one is cost. So running agents is still not cheap, especially as you're doing these long inference jobs with chain of thought constantly. Turns out that ensembling agents together tends to improve performance, so everyone's just throwing a lot more compute at these things, but the cost of running these agents is still quite high. So an example of this, so we run our API, 03 is usually around 40 tokens a second. At our current price, assuming only output tokens, by the way, I'm assuming input tokens are all cash and basically free. If you're running it constantly, trying to do some agentic task, this translates to around $27 a month. Which is not that bad, but it's also, as you run a bunch more of these, it starts adding up. But the good news is, obviously, these prices are going down very quickly. I think this is the combination of 4 different factors. One is, model distillation improvements on the research side. 2, inference tricks and improvements, around KV cache optimizations and things like that. Third one is hardware optimizations that a lot of the chip makers are doing. And the fourth one, which I actually think may be driving the most recent precipitous decrease in cost, is how willing these large providers are to lose money on these models in a price battle. But 900x a year price drop is pretty crazy. And so what will happen when this $27 a month thing goes to $2.70 or 27 cents per month? I actually think we'll be in this world very, very soon. And so to cap things off, where can we go from here if we solve these? These 4 areas would then be kind of fixed. Imagine a world where agents are able to connect to everything in the world that a human can and do valuable work. Imagine agents that can generalize well. You can drop them into any new environment and learn, and it can learn how to be effective. And it just like you dropped into some workplace, learning all the different tools. People in every corner of every organization can create and customize agents. And the best part, you can run fleets of agents without any consideration of cost. Cool. So the end state of this, a personal AI assistant for every human, a context-aware AI at the center of every business, and millions, billions of mini agents running around to fill the gaps. So it's an exciting time, and yeah, thank you.
That was a great set of talks. How's everyone doing so far? Good. So before the next great set of talks, I will share very quickly about my vision about the frontiers of agentic AI. It's going to be high level and short, but I will speak slowly. So picture an assistant, agent, digital companion, or stand, whatever you prefer, that grows, learns alongside you, and collaborating with other sub-agents to tackle any problem. When I started working on agentic AI in 2023, I dreamed of an AI system with natural interface, strong capability, and scalable architecture, an agent that evolves through interaction. I created AutoGen, now AG2, to contribute to that vision. Now, the whole industry has made huge progress in the past 2 years. Where are we now, and where are we heading? Interface. Today's AI is gaining sight and sounds. For example, Gemini Live can use your camera to see the whole world during the conversation and speak to you in real time. They can also see your screen and trigger actions by your side as you use your device. These advances narrow the gap between intent and understanding. But to reach our North Star, context must flow across devices, and agents must know when to engage or to step back. Understanding is only half the battle. Agents must act. Coding assistants like Claude Code, Gemini Cli integrate into developers' workflow, autonomous writing and refactoring code. ChatGPT agent blends browsing, execution, document creation into a single flow. Why is coding a big deal? It's a meta power. An agent that can exchange its own software can self-improve, experimenting, learning, and spawning new sub-agents. To realize this, we need cross-session reflection, long-term memory, and learning by interaction, like what Matei suggested. Breakthroughs will come from collaboration among diverse agents. AG2 orchestrates multi-agent teams. MathGen, a very new open source project I just introduced in the Frontier stage, pushes this further, running agents in parallel, observing and refining each other's work. Grok Heavy has shown it's won complex challenges like LAX human exam using this approach. Gemini DeepMind won IMO Gold. And ChatGPT, Cloud Code has sub-agents and ChatGPT agents, and so on. Imagine scaling recursively. The potential is exponential, but we must solve consensus, shared context, and interoperability. Natural interfaces turn intention into understanding. Strong capabilities turn understanding into actions and self-improvement. And scalable architectures allow many minds co-creating solutions. By weaving these layers together, sensory richness, multi-agent frameworks, and self-modifying code agents, we glimpse the AI that doesn't only answer questions, but grows with us. Thank you. Let's welcome the next speaker.
Oh, perfect. OK. Sorry, let me go back one slide. All right. Hey, everyone. I'm Jerry, co-founder, CEO of Llama Index. For those of you who don't know Llama Index, we are a developer platform. We give you, as the developer or AI engineer, all the tools you need for document processing plus workflows. So today, I'll try to keep it very short and sweet and actually keep it within 5 minutes. So I just got my timer right here. We're going to just talk about some high-level architectures that are emerging in terms of like agents and how they actually help automate knowledge work. So first off, I'm sure all of you already know this, but models are like blank slates, right? So even if the model is really, really good, they're getting better and better, but they really require you to actually supply the prompt, tools, and other metadata so that you can actually achieve the task at hand. The biggest barrier to AI value is your own ability to use AI effectively. Even if the model is really good, if you don't know how to use it, you're not going to get good results. How many of you guys have heard of context engineering in the past few weeks? OK, so like half of you. Basically, if you suck at prompting, you're not going to be able to use AI effectively. Now, just imagine you're kind of like a naive user of ChatGPT, and you just say something like, give me a financial report on Apple, just like a really simple, dumb prompt. There's nothing else. There's no tools, no user prompt, or kind of like no system prompt, no multi-step workflow. Obviously, it's not going to give you very good results. The results are probably not going to be tuned to your user preferences. If you're in an organization, it probably doesn't follow the standards that your company has set out, and it doesn't actually mimic the steps of an actual human worker. And so automating knowledge work requires actual proper context plus workflow engineering. If you imagine kind of like an overall AI agent following a runbook, you really need two things. One, you need the right context and tools for any sort of agent reasoning loop. And then the second is, especially in the enterprise or in the workspace, you want some repeatable pattern that you can encode as a workflow. So first is context and tools, which I'm sure you guys have heard a lot about and also have heard about the importance of context engineering. But it really is pretty simple. It's really just how do you supply the right tooling so that an LLM can kind of access external services and also get back information that can feed into the context window. If you look at any general agent reasoning loop, this includes applications, your favorite ones, whether it's OpenAI, ChatGPT, Claude, Manus, Deep Research, Perplexity. Anything that has like an overall text input for you is basically like a general agent reasoning loop. And if you just equip it with the right set of tools or MCP servers, then the end result is that the agent can actually access the external world for task-specific context. The main limitation of this for actual proper kind of adoption of AI is that you as the human are still responsible for defining the actual input so that you get AI to do what you tell it to do. The main thing with all these assistant interfaces is it's completely dependent on you, the user. And so if you're not good at prompting, you're also not going to be able to use these types of tools effectively. Just on a side note, especially since probably 2 years ago I was on stage talking about like RAG, I think in general there's kind of like a meta architecture that's emerging, and it's really just around what are the agent reasoning loops and what are the tools. And so if you think about just like access and context, instead of thinking about it as RAG, I would really just think about it as a set of tools, whether it's retrieval, file lookup, manipulation, and other things. So if you want to access your docs, imagine just like a file system like the MCP server that you see on the open source, or just some set of like kind of tools that you plug into an agent in order to inject the right context into the prompt. Level 2 is workflow engineering. And this is something that I feel like people implicitly talk about, but they don't really talk about as much as I would expect. And it's really about, instead of just providing a super general interface for a human, how do you get an AI agent to actually encode a proper workflow, output that as a series of steps and enable repeatable use, not just for you, but also for others. And so we're kind of seeing examples of this throughout different enterprise use cases, whether it's like invoice processing, contract review, financial analysis, due diligence, and more. And so the goal is to actually define a constrained series of steps where you actually, as the user, define kind of preset prompts for the agent to follow while there's still pockets of agentic reasoning in the middle. This allows you to basically encode some overall process as kind of effectively like a DAG or some overall workflow architecture. And the benefit here is, you still probably need human in the loop at the end to review the results, but it's not completely dependent on your ability to just like prompt it for basically every step of the workflow. In contrast to something like deep research, the advantage of this is once you define the workflow, you can basically repeat it, kind of like a computer program, and just have other people use it without them also having to spend the brain cycles figuring out how to use the workflow. And so, at the end of the day, one of the values of frameworks, and the frameworks have evolved over time, but one of the core values of frameworks is to help you like define these types of workflows, so you can actually standardize an agentic application within your organization. This is just a kind of example architecture of kind of maybe doing some financial extraction over a document. You might want to split it. You might want to do some kind of like extraction over the financial tables per document, and then synthesize everything in a pandas data frame. That is a series of steps you can encode as a prompt, feed it into Cursor, or just like implement yourself in Python, and then you basically define kind of like an overall DAG of a sequence of steps that you need to follow. Last topic is just like the idea of MCP, which is obviously very related to this whole thing. If you define some automation workflow, you can not only just encode or provide context as MCP servers or tools, you can provide entire workflows as MCP tools. So one of the advantages of this is imagine you go to your favorite tool. I like Claude, but you go to Claude, and then instead of me having to figure out how to write this like giant text prompt, I can basically feed it my favorite MCP tools that basically routinely operationalize like certain things I like to do, whether it's scheduling a meeting or kind of like responding to an email or processing a document. And then I basically offload the mental burden of this to the tool itself so that I can actually achieve the task at hand. So that's basically it. And yeah, thank you very much.
All right, good afternoon, everybody. Officially afternoon now. No, we have 1 more minute left. I'm Matt White. I'm the Executive Director at the PyTorch Foundation and the GM of AI at the Linux Foundation. And I'm going to share some thoughts today with you very briefly on open source and open standards and an agentic realm. So a quick note on AI and open source AI at the Linux Foundation. Open source AI is very alive at the Linux Foundation. We have a lot of really fantastic projects. Chief amongst those, PyTorch, Kubernetes, VLLM, and other really great projects that are really advancing and accelerating the open source AI space. And generally, people don't think about the Linux Foundation as a place for open standards, but we actually have more than 200 open standards, including OpenUSD and C2PA. And we have a few more projects that have come down the pike lately. And so we've got Google recently announced that 8A protocol is now a part of the Linux Foundation. And we also have Agency, which is Cisco's project, which has support from Dell and a number of other companies as well. And so we're looking at like what do we need to do to make an open agentic future, right? And we generally know that open source has eaten the world already. And open models are now eating open source. And open agents will fundamentally eat everything, right? And so part of this is going to be doing open source like the right way. And that's really, solve real world problems. Don't sort of make bombastic claims about you've replaced 80% of your workforce with like collaborative agents and all of this. Like, it doesn't really help the industry. I would say innovate and differentiate your project. If you don't have a substantial ability to innovate and differentiate from other projects, then I would advise you to join existing projects and become a contributor. Build a strong community around your open source projects. This is what makes them successful, especially being humble and having the ability to accept user input, accept feedback from the community, and really work to solve the problems that your community is presenting to you. And I would say also choose an appropriate license. So folks have been using MIT and Apache 2.0 for a long time. We've gotten very accustomed to that, but now we're using it for models. I would share that the Linux Foundation has released an open MDW license, which is here for solving a lot of the licensing issues around open models, which are not software, right? We're talking about both code and high-dimensional data. And define a clear roadmap, like publish that on your GitHub repo, also share your office hours, engage with the community. I think a lot of projects struggle because their benevolent dictator says, hey, we're just gonna, this is the way we're going and get on board or don't, right? So, and then obviously documentation and tutorials are certainly essential here. So my time is up, and so here's my small agentic wish list. It is an excerpt from a very long wish list, but I would say, a few of the things that I think are really important are going to be, alignment and standards and protocols and schemas. Like, let's work together to create standard formats. There needs to be a stronger security focus. Right now, there's really cybersecurity is kind of absent from a lot of activities in the agentic space. And it would be great to see more agentic functionality built into models themselves. And so, this is where K2 is kind of emerging. And then observability and tracing. So it is really hard to debug a lot of agent workflows. And so, focusing on providing debugging functionality and test harnesses is really important as well. And with that, I would invite you to add to your calendars this year that we will be launching the first Open Source AI Week. This will be October 18th to 26th this year. If you have an event, please feel free to submit it. And also, the PyTorch conference will be taking place October 22nd to 23rd this year. All right, thank you very much.
All right, hello everyone. I'm Brad Axon. I'm a principal engineer at Block, where I work on data and AI. And I'm going to talk through some of the things that I think will really matter for improving what agents can do for you as an individual over time. And the way I'm going to do that is by walking through the interface of the open source AI agent that we're building at Block called Goose. So let me get this started. Oh. If you could play the video back there. Okay, great. So I think this has been covered in a lot of the previous talks, but one of the things that's most important about agents is that you should be able to define what they're capable of doing. And Model Context Protocol is a really valuable way to do that. Because it's a protocol, that means that you as an individual at any time can just extend what an agent like Goose can do for you. And you can see I have a very large number of things that I use for it occasionally. And I think this is critical because you can connect the different systems that you use to do your work. And so you're not just locked into one specific use case, you can do several. So in this case, I'm going to turn on the Databricks MCP and a developer MCP so I can use this to analyze some data for me and then make a website. The second thing that I think is critical is having access to all sorts of different models. So here, I'm going to go ahead and switch this over to use Qwen 3, which is a fantastic coding model that was released just about a week ago. And once that's set up, I'm going to get it started, asking it to check on year-to-date internal usage of Goose and then make a website to show that off. So OK, so while this is doing the work, what I think is so valuable about having the flexibility of picking different models is that you can kind of stay on the frontier of performance. So of course, there's like big major model releases every couple of months right now. And each time, it's a major jump in what the agent can accomplish using the power of that model. But I also think that we're increasingly seeing that people have preferences for different models in different cases. And you might, in the middle of a conversation, want to switch from a coding-specific model like this one to something that actually is better at writing. So you pick off from where you left off on the data analysis and then move into writing a report. And so those things, I think, push the performance frontier by giving you the best models for every given task that you need to accomplish. OK, so at this point, it has run a query, and I think it has gotten the answer to the question. And now it's actually working on the code. And so while it finishes writing the HTML, the last thing that I think really matters for making agents for individuals is, again, open source. So I think open source has just this fantastic track record of making software that lasts and also giving everyone access to that software. So I think making the agents open source both makes sure that you as an individual have long-term access to it, but also that we can kind of collectively improve it and have a conversation about what it needs to do. OK, so at this point, it has, I think, finished the first draft of its HTML. In just a second, it should do the last final edit and open that up. OK, so this is all from scratch. This is what's exciting about this. All I gave it access to was a database and a text editor, and it made a dashboard for me. It didn't need more complex tools because it can combine the things that I know it needed to do. And I think that just shows how you can build this up to larger and larger use cases. OK, thank you.
Check. OK, that's great set of talks. Let's just dive into the panel. Yeah, by the way, this is the first time I moderate a panel that only consists of human speakers. I used to mainly just orchestrate agents, but this is I guess it's much harder. So I have a few questions, and then after that we can also open to the audience, I think. For each question, I have two versions. Okay, so one is AI version. One is my own kind of phrasing of the question. You can pick any one of them. I would just ask both. Okay, the first one. Let's talk about game-changing AI agent. Okay, the AS version of the question. What is one AI agent or system you've recently encountered that's transforming how we build or deploy agentic systems? And what makes this framework or stack stand out? Okay, that's AS version. And my old version is, name one AI agent you recently used and thought was a game changer.
Okay, so so one system I think I used a bit recently, and also, but more my students. Now, so one system I used, Agentic system I used recently, which I thought was pretty cool. Although my students use much more, and I know from them quite a bit. It's OpenEvolve, which is AlphaEvolve clone in the open source. And why is that? Because actually you can use it to come up with, say, some algorithms to optimize systems, which, you know, maybe in the previous years were good enough to be part of scientific publications. So if you extrapolate that, you know, this means that, you know, we are going to do more and more research using these kind of systems, and we are approaching that, you know, tipping point.
Yeah. Great. Anyone else?
So there's 3 panelists here that have agentic frameworks. So I'll say all of them are great. I was on PTO for 2 weeks, and so in the AI world, that's like a century. And it looks like I'm really interested in checking out this wide research by Manus AI and seeing how it performs compared to some of the deep research platforms. There's also, I saw deep agents as well, and I'm curious to see how that stacks up, because I'm very interested in, you know, a lot of these platforms, a lot of the frameworks struggle a bit with the like deep research type activities and being, you know, accurate and consistent. And so those are a couple I'd like to check out.
Hello? Yeah? Okay. I was going to say one obvious answer, I think, is actually MCP as a framework. I think it's been fantastic. It's super general. It's taken over. You can just put it in front of, you know, anything, and there are all these public servers that are out there. So I actually think MCP has been a really big boon for the agent ecosystem. I actually think there's still more to kind of figure out and dig there as well. Like, I think there's a lot of best practice around like how to create an MCP server, what functions and tools to give the model that are best, that I think we still need to figure out. But just the fact that we have this general, you know, like framework that can sit in front of any tool and talk to any model, I think is really great. And then the answer for the agent, I just use Cursor a lot in agent mode for all my weekend projects. It's just yeah, the vibe coding and just like letting it run loose on something that I'm trying to build has been really helpful.
Yeah. I mean, I can speak more. I mean, we have an agent framework, and so, you know, I would be a little bit biased there. But in terms of like the agent application, to echo Sherwin's point, I've been very interested in just like vibe coding recently. I'm sure many of you already do that, but like basically, I think the high-level idea is that the line between a programmer and a non-programmer is like pretty much blurring. Like if you know English and you can define a prompt, you can encode some sort of workflow, and then basically use that to generate some sort of you know, application for you. And I'm personally very interested in how you can use these tools like Cursor, Claude Code, Windsurf, to basically generate agentic automations, because it's like AI generating like kind of more constrained AI for your personal needs. And I've already started doing that. We're probably going to put out tutorials on how you can do that with our stuff. But yeah.
So I think, obviously, I have to say Goose is great, but that's our agent. So I'll talk about something else instead, which is an MCP server that I think really changes how vibe coding works, which is Playwright. So this is for web, and it gives the agent a mechanism to more or less see what's being rendered like at the DOM element level and then manipulate them. And I think it turns it into this feedback loop where it can build just shockingly advanced projects, and it's that feedback that it brings back from the visual layer into the code. And so I think those kinds of innovations are where they're going to get us to a place where you can take on bigger and bigger projects.
Yeah, I think all the vibe coding agents have really been changing the way me and also my students and other people I work with are doing things. Cursor, Claude Code, Goose. Really, honestly, I don't see like a huge difference between them, but you know, they're all getting better, and the new tools are making them all really good.
Right. So we have Alpha Evolve, we have Deep Research, Deep Agent, MCP, and vibe coding. Great. That's great answers. The next question, let's talk about unmet capability. The AI's version is going to be, what's one capability you wish agentic AI systems could achieve today to revolutionize their frameworks, but they currently cannot, and why is it critical? And my version is, name one thing that you really wish an AI agent could do, but can't today.
I think one, I'll say two things, because we work pretty closely in this space by providing tools for developers basically build various types of agentic applications. And part of the goal of like providing any sort of framework is making sure that it's actually useful to you guys. Like there's certain pieces, especially with like vibe coding these days, that honestly like some parts of frameworks are not very useful anymore. And then other pieces could still potentially be relatively useful. The parts that aren't very useful are just like the wrappers around integrations, such that you like have some like Llama Index LangChain wrapper over OpenAI Anthropic. It's kind of like useless at this point. You can just like vibe code some API integration with OpenAI directly. The parts I think are still useful though is I feel like we haven't figured out the right abstractions for like a simple abstraction for how you actually inject context into an agent. And it's just like some simple memory management layer. Everything I've seen is either way too opinionated and you have to pay for, or it's like, it just doesn't actually give you enough things for you to actually do anything with it. And so that plus like this idea of MCP servers, and for us, we're very interested in documents, this idea of like being able to navigate certain files, inject those into context, and traverse like just massive volumes of context, I think are still missing from the framework side. But we're very interested in kind of building towards that.
So this was definitely the answer. This was also the answer that I wanted to give, which is memory. I think in general, like context management is the hardest problem with agents, and what you expect something that you work with every day to like remember and reuse is very far from what we can achieve right now. So you're starting from scratch. And I genuinely think that we don't have the right algorithm yet. Because imagine trying to do your job where you never remembered anything, but you had good search tools. It would be impossible. And so search is not, I think, quite the right shape, but I wish I knew what the answer was. I think that would be a very valuable answer to have. But I think we have to figure out, as almost a research area, like what is an algorithm that gives memory to the context window that actually can like span days and weeks and months of iteration.
2 votes for memory so far. Anything else?
I'll say a different one. I'm surprised basically that we haven't really solved hallucinations. Like models will still say things very confidently, and then we're building these UIs where people can review stuff, but it seems hard to solve that. So if you were to solve one thing, that would make a lot more reliable applications.
Hallucination. Okay.
Yeah, again, I'll say, and I'll go back to what I'll say, and I'll go back to what I said in the talk. I think reliability is the number one for me. Problem needs to be solved. And the hallucination I just shown Matei is like I was trying to do something for my slides. I didn't include in the slides with the top companies by market cap. It's a very simple question, right? And I'm not going to say the name, but one of the top models, top 2 or whatever you want to say, it just hallucinated. He was not able to give me the top 10 companies by market cap. And when you ask it, are you sure? Because obviously it's a mistake. Actually, the way I started, I started asking for market cap, the top 10 companies by market cap from 1955. And I guess something with AT&T is the first place. I don't know what happens there, so I don't even, it's fine. But then I thought, oh, let me ask also for today, because for today I kind of have an idea, and it was missing from the top 10, Google, Alphabet, and Meta, right? And when you ask again, it's like, are you sure about that? What about this? I say, oh yeah. I'd give you the correct one. So maybe one thing is that they should say when they don't know that, right? They could say, I don't know. So I think that's going to be one of the things, very important things. But again, we need to somehow make progress in that, on that aspect. And when I was talking about specification, in some sense, all this kind of, who says about the prompt, you don't know how to ask to construct the prompt, well, good luck, right? But the prompt, whatever we do, is actually adding, it's specifying more details what we want to get from these models. And if you think about many of these agentic systems, and you have multiple LLMs collaborating, what you do actually, you build a system, you build a prompt, appending to the prompt and so forth to come with the best prompt for the last, in the pipeline, for the last LLM in the pipeline to give you the right answer. And including that kind of trying to get more context and things like that.
Yeah, I would echo Matai and Ian that definitely reliability is that one issue that still hasn't been solved. And if we can't solve it with LLMs, can we really solve it with agents? That's the question to be answered. Also, there's also something related to that, which is consistency, right? And so if you're not getting consistent experience, the end user's not getting consistent experience, the interaction between multi-agent systems is not consistent. Obviously, reliability is a factor there, but consistency and especially around the multi-agent frameworks, right? Jan spoke beautifully to a lot of these challenges right now, and there's a lot of it's a lot of opportunity. There's a lot of things that are unsolved in this space, and I think it's a great time.
Yeah, reliability is a big deal. One way I'm trying to overcome that issue is I use multiple AIs. If I don't trust any single of them, I will cross-check. And that's actually the idea behind the MassGen project that I just introduced.
But they're all being trained on the same data, so that won't work.
Actually, one of with LM Arena, one of the kind of killer use cases, people coming, like for instance, students, and asking to solve their problems. And it is talking with a few of them. The killer feature is that they can get 2 answers. So if the answer is kind of the same, they have more confidence. Oh, this solution is good. And if the answer, even if the answers are different, then they can go into more details to see where they are different. But
yeah. Cool. Yeah, that's a fun discussion. So next question about technical blocker is related to the previous question. The AS version is, what's the biggest technical obstacle in building or deploying an agent with this desired capability? And how might advancements in frameworks or stacks address it? And my version is, what's the biggest technical blocker to build or deploy such an agent?
I do kind of think you don't really need a lot of framework stuff if the LLM is sufficiently good. Maybe it's a hot take, but if you have a model that's sufficiently good at reasoning with like an infinite context window, honestly, a lot of the context engineering stuff is kind of just hacks, and so you're kind of like banking on the model getting better over time, such that there's no like loss in the middle or context rot, and so as a result, the agent architecture itself can actually simplify. I do think in that world, in general, the job of like you as an AI engineer is less on kind of like hacks for context engineering and more on just being able to translate the actual like business requirements or like the task at hand into like a prompt or some workflow with the right tooling and context to solve the task. So I think in general, like I think like as models get better, that is a technical blocker. You can actually simplify a lot of the ways you do orchestration today.
Yeah, I guess, Sherwin, you already mentioned quite a few in your talks about this question.
So I think, again, is like, and again, I would go back, and I think it's really similar what I'm going to say with Jerry, but you need to learn, and we need to learn better about how to specify, how to be more precise with our prompts. Because this is how we do in humans, like in your team with humans, right? It's like, and it's like the effectiveness of your team, it's also driven by how well you communicate with the people, right? How well you specify what you want, and also, what does it mean success, okay? If I tell you I want something, I need to tell you also something, what does it mean a good job for that task I mentioned to you? So I think that's kind of is going to be more and more, it will be the focus as the LLMs are going to be more and more powerful.
Yeah, I'll say my answer is I think related to all of these, and it kind of touches on like this generalizability piece. But one thing that I think is a technical blocker is I would love to see these models be able to increase the time horizon in which they can have coherent reasoning and thinking. I think as this gets longer, you can solve, it's like not super elegant, but like it's a way to solve consistency, reliability as it's like checking itself. I think memory has a component to play here too. It's like as it's reasoning over, should be able to learn about the tools that it's using, which one doesn't work, which one does work. Just like how, you know, if you're a human dropped into a new workspace, you kind of like poke around and use that. And this kind of moves us towards a world that I think we might end up where the model is just really diligent, very smart, and just like a human, you know, you give it some tools that might not be that great, not the best searcher in the world, but it'll just diligently try and find and do the task for you. But I think it's just not very possible right now because these things can't really go beyond, you know, I'd say like tens of minutes. But once it gets longer than that, it'll be really exciting.
I have a random question for Sherwin. Do you think memory should be handled at the model layer or like outside of that?
I think outside of it. I mean, so we've explored a lot with memory internally, and everything we've done is done outside of the model layer. Also, anything, once you start touching the model, it gets very expensive and, you know, a lot more complications, and we've seen good things just from outside.
Gotcha.
I also think like the project that Matej talked about too is a good example of this. Like, you know, it's even just at the prompt side, you can just really guide it and almost give it like a memory of from the policy and have it improve.
Yep, makes sense.
One different take on this is that I think we're dramatically underusing the capabilities we already have. And the main reason I think we have that problem is that access and connectors. Like, so MCP is, I'm very confident is the solution, but we need more of them for all the different like third-party things that you want to interact with. And then the better that gets, the harder just identity on the internet is the like major limitation that I think the industry needs to do better on, of like, hey, I just want to give this agent access to everything I can do without having it be 75 different OAuth flows or whatever it is along the way. And that's a very tractable problem, but I think it takes a lot of industry movement, and agents make it much more valuable than it was 2 years ago.
Great. We have very diverse perspectives for this question. So we have 3 minutes left, so let's do a rapid fire kind of round. For the next 3 questions. So AI's future edge. What is one task where agentic AI underperforms humans today, but you expect it to surpass human capabilities by, let's say, August next year, or the same time next year? And what stack improvements will drive this leap? And my version is, name one thing that you're confident that the AI agent does worse than you today, but will do better than you by the same time next year.
So my hot take is I actually think they're not like that great at coding yet, even though, you know, some of these agents are out there. Like, you can actually, I think it's like a mid-level engineer. You know, some of us are senior level engineers, and so I think definitely by next year coding will probably surpass that.
I think form filling and anything that requires manual data entry. I think humans are probably better at it right now, and also you would trust a human more. LLMs are certainly faster, but they're just not as accurate. But I see them surpassing humans.
I think we might be surprised that they excel at scientific research in the next year or so. There's a lot of investment being put in that space and a lot of research and you know, very specific domains, right? We could see something really, you know, emerge out of that.
I think vision is actually surprisingly bad now. VLMs have all these sort of holes in understanding. I think it's very tractable to improve it.
And both of those combined, I think data analysis and dashboarding, it's very close already.
Yeah. Let's quickly move on to the next question. Please. Sorry.
So yeah, I think that a non-trivial number of, again, algorithms which are in this publishes the top conferences in, say, systems, networking, databases are going to be, is going to be possible to do with this kind of new systems, agentic systems.
Yeah. So I think we're at the time. So let's thank all the panelists again. That's great insights. I hope you enjoyed the session. Thank you very much.
Hi, everyone. Please return at 1 o'clock for the afternoon session that will begin with a keynote by Professor Don Song. And remember, lunches are served on the patio upstairs on the 5th floor, as well as downstairs on Lower Sproul Plaza in the 10th. So thank you very much for joining us.